Therefore, efforts have been focused in the literature in alternative description of such configurations, and these include regular black holes, which are basically trapped regions of space-time with horizons, but without singularities, and also horizonless or solitonic configurations that are devoid of both horizons and singularities. So I will mainly focus on regular black holes, and I will describe some effective ways to actually source this type of solutions. So here we will have the Einstein-Hilbert action, and varying this action with respect to the metric tensor, we will get the Einstein equations where the left side will be the geometric part and the right side will be the matter part. So in order to source regular solutions, we need to actually modify this in some way. We can do it by modifying the gravitational sector, by having some higher order curvature corrections. So this can be done through Lovelock theory or through quasi-topological gravity that I'm mainly going to talk about today. So the second way to actually generate these solutions is by having additional matter fields. And one of this way to do that is by nonlinear electrodynamics that I'm going to describe later on. So in Lovelock theory, we have generically second-order equations of motion. And the Lagrangian density looks like that, where we have basically a series of curvature densities that are described by linear combination, by a combination of Riemann tensors. And we have this sum being truncated at some finite k, where it depends on the dimensionality of the spacetime. However, there have been a recent paper by Fernandez where they have used an infinite sum to generate regular solutions in 4 dimensions. So if you're interested in that, you should have a look in this paper. So example of these curvature densities will be for k equals 0 will be the cosmological constant. For k equal 1, we'll have the Ricci scalar. For 2, the Gauss-Bonnet, which will be topological in 4D. And we have the cubic term, which is topological in 6 dimensions. So today I'm going to talk about quasi-topological gravity, which is slightly more general, and it applies for space-time dimensionality greater or equal than 5. And the action has this form where we have this Lagrangian density, and varying the action with respect to the metric tensor, we get some modifying equations with a modifying geometric part. So the Lagrangian will look like this, where we have the typical Einstein-Hilbert action, and we have some corrections that are encoded in these curvature densities Zn. And the difference with Lovelock theory is now that we can have an infinite sum, or n is not restricted by dimensionality of space-time. And this is a main difference that I will use to source regular solutions. So we have that the geometric part is of this particular form. And this ugly expression, as you can see, has this term over here, which ultimately leads to higher order derivatives of G mu nu, specifically of 4th order, which is related to maybe Gauss, and we want to eliminate this term. So by eliminating this term, we can do it, first of all, generically. Doing it generically leads back to Lovelock theory, but we can also pick it to this term to be 0 only on a spherically symmetric background, and this is what we're going to do today. By doing that, we get some densities Zn, which are different than the Lovelock theory. So to give you an example how we source regular solutions, assume that we have a metric that looks like that. And if we want to add matter fields, we assume here that they will inherit the spherical symmetry of the spacetime. And the equations of motion will look like that, where, as you can see, we have function h psi here, which is basically a series expansion that's like that, where these alpha n are related to the alpha n that shows up in the action of the theory. So the interesting thing here for quasi-topological gravity is that once you integrate one of these equations, basically you need to solve an algebraic equation for psi. And doing that, you can immediately find the metric function f of r. So if one examines what's the behavior of f of r close to the center, you will see that has this particular form here, where if we take the summation to go to infinity, immediately you will see that this behavior will be similar to a de Sitter core, which is a main requirement for regularity. So an example will be basically vacuum solution. So the right part will be 0 here, and we have a function h of psi of this form, where basically we have picked a specific resummation with alpha n having this form here. So integrating once, we find that f of r has this form, which is similar to a higher dimensional Hayward model. This solution is unique because we have a Birkhoff-like theorem. And we can also modify this by assuming other matter fields. We can have cosmological constant, and we can have other matter components as well. So this was the first part where I talked about modifications of the gravitational sector. We can do it by modifying also the matter sector. And here I'm going to include a Lagrangian density of this form, where F basically is a field strength that arises from the contraction of the electromagnetic field tensor. And in order to source regular solutions, basically we need a magnetic charge. So by having no electric charge, we will have a four potential that has this form over here, and F mu nu is given in the usual term. So having that and solving for a metric function in a spherically symmetric spacetime, we can actually source regular solutions. So a first example will be the Hayward model, where we have this metric function, and by picking a Lagrangian density of this form, where you can see we have an additional parameter alpha, we can pick the parameters alpha and the magnetic charge in a specific way that we can actually source the Hayward model. Here, the weak field limit of this Lagrangian is stronger than the Maxwell limit, and this is an unpleasant feature of this theory, but the model I'm going to use will have this limit, as I will show you in a bit. So Bardeen model can also be sourced within this framework. We can pick again the parameters alpha and the magnetic charge in a specific way, like that, to source the model. And the model I'm going to use is basically one introduced by Cadoni and his collaborators, where we have a Lagrangian density that gives the weak field limit, which is the Maxwell, and this avoids some causality issues. What I would like to emphasize here is that in all cases, the regularization parameter L, which basically when it goes to 0, you immediately get the Schwarzschild model in all these metrics, is connected to the presence of the magnetic charge. So we need the presence of a magnetic charge if we want to maintain regularity. And now I'm going to proceed with thermodynamics. So we studied the phase structure of these models. First of all, we did that in 4 dimensions. So we have here a parametric plot of the free energy with respect to the temperature. And here we have a small to large first order phase transition, which terminates at a critical point over here. And this is the typical swallowtail behavior that we see also in Rice-Nostrom cases. So here, the Hawking-Page transition will not be present because we have a magnetic charge, and working in the canonical ensemble means that the F equals 0 line, which represents radiation, will be inaccessible. However, the situation will be different within quasi-topological gravity, where despite the fact that the parametric plot has exactly the similar structure as the 4-dimensional one, here the presence of magnetic charge, the magnetic charge is absent, and this means that the F equals 0 line will be accessible, and therefore Hawking-Page transition will be allowed in this particular case. Interesting behavior also arises when we have t equals 7. We have the presence of a triple point. So this point basically represents a coexistence of a small black hole, a large black hole, and also radiation that you can see from this black triangle over here. And the termination of this transition ends here, with this second order transition is physical because their free energy is negative. Interesting structure also arises in t equals 9, where we have for a particular choice of the regularization parameter, we'll have the small to large first order transition, which terminates again at a critical point. So for a generic case, we can have within quasi-topological gravity an equation of state that looks like that. And I want to remind you that for the van der Waals case, we have an equation like that, where we have a parameter B, and this represents a finite size of molecules, while we also have a parameter A, which represents the interaction strength between molecules. So for the Hayward model, this generic relation will be translated like that, where you can see we have a parameter alpha, which leads to an infinite pressure, and this will basically represent a finite volume. So one can generate this, we can redefine a reduced volume V, and also the parameter B in this case, and you can see that B is directly related to the coupling. So we have a finite volume that is directly related to the regularization of spacetime, and this particular case is mostly generic because this H prime psi plus will basically diverge in a specific horizon radius, and so this will be a generic feature of such theories. So I'd like to conclude my talk. So we've seen some regular solutions that within quasi-topological gravity, we didn't need any fine tuning of parameters, but we need in nonlinear electrodynamics. We saw some interesting phase structure depending on dimensionality of spacetime and regularization method, a finite molecular volume for the case of quasi-topological gravity, and we have more interesting result in this paper, so I recommend you go and read our paper. Thank you very much. Yeah, sometimes it works, sometimes it doesn't. Yep. Uh,
Is that necessary that it wasn't called remedy instead of the law or something?
so for Lovelock, it can be done, but we need a modification of the curvature densities in order to have contribution in every order. So this is what Fernandez did. So as you did for d equals 2 case, you basically have some correction that leads to contributions in the equations. Yeah, I can use that as well, and I think I should. Yeah, so you can have it in Lovelock theory as well in 4 dimensions, but you know that in this particular case, we only have the Gauss-Bonnet term, which is topological. So in order to have contribution, we need to modify these curvature densities by an additional term, which is conformally related to the original metric. So doing that, we can actually source the solutions. Fernandez did it only for planar case because the equations of motion cannot be integrated for spherical or hyperbolic cases. I think this is similar with just the cubic theory as well. So I don't know if there will be any progress in that later on. Yeah. Mhm. Yeah. Ye- So you mean with purely Lovelock theory, or you mean so only by adding some additional densities that will make every term contributing to every order. So if you don't do that, there will be no contribution. because of topological terms, and the expansion needs to be truncated somewhere. So as you can see here, so you have a finite truncation of these densities, and this depends on the dimensionality of space-time. But if you modify this LK by terms that don't contribute to the equations of motion, you can actually show that everything contributes with a dimensional regularization of the coupling at all orders. Doing that infinite summation, we can source regular solutions. So if you're interested in that, have a look at this paper by Fernandez. It's a very interesting one. But we only have the planar case that is solved. The other ones are not solved. Thank you. No, yeah.
Now I'm gonna solve this problem. Relation table. Okay, here. All right. Hello, everyone. Thank you. So today I'm going to tell you a bit about the research I've been doing with my supervisors, Andrei Frolov and Gabor Kunstatter, on evaporating regular black holes in 2D gravity. So this talk is going to be a lot more relativity than quantum, but the motivations come from quantum information and specifically the black hole information loss problem. So famously, Hawking's prediction that black holes emit radiation leads to the conclusion that the process of forming and then evaporating a black hole is non-unitary. So over the decades, there have been a lot of interest in this problem and a lot of proposals to resolve it. But today I'm going to be focusing on one proposal that links the problem of information loss to the singularity that appears in black holes. The basic idea being that if the space-time is globally hyperbolic and there's no singularity to act as a sink for information, then a distant observer should be able to recover any information from the black hole. Or to summarize, as Hayward put it so succinctly, what goes in must come out. The problem here is that a lot of classical models of non-singular black holes have their own issues. So not least of which is that they're not globally hyperbolic. In addition, they're subject to a lot of instabilities, which could lead to diverging terms and introducing new singularities possibly. So in order for regularizing the singularity to actually be a viable solution to the black hole information loss problem, we have to make sure that these issues aren't present in real regular black holes. So to that end, we've been looking at regular black holes in the context of 2D dilaton gravity. So we begin with this general action up there, consisting of an arbitrary function phi of a dilaton field R, which basically just plays the role of a radial coordinate. And this theory has a one parameter family of static vacuum solutions given by that metric here, which is just basically the Schwarzschild metric, but now with this arbitrary function J of R. And to model the formation of a black hole, we glue together two of these static solutions, so an interior solution with m equals 0 and an exterior solution with m greater than 0 across a null surface, and that gives this picture there. So you have the shell in yellow coming in as it converges, it creates an apparent horizon in green, behind which is a singularity. So the last talk discussed different theories that could actually produce regular black holes. But for our purposes, I'm just going to assume that we can make J whatever we want and tune it in such a way to give us the right behavior so that we can actually just create a regular black hole with space-time. And of course, there's a lot of different ways we can do this. But as a specific example, we're going to use the Bardeen metric, which is given up there, where L is just a regularization length scale. So on the left, I'm plotting the components of the metric. And far away from the black hole, a large R, it just looks exactly like the Schwarzschild solution, which I had better, because we know that the Schwarzschild metric is a good description for black holes, far away at least. But close to the center of the black hole, it shows very different behavior in the metric, and the result is to keep the curvature on the right from exploding. So I have a diagram here of what that looks like. On the left is the Penrose diagram. So we have the shell coming in yellow. Now, instead of a singularity, we have two horizons in green, bounding a trapped region, beyond which is an untrapped region. But we also have a Cauchy horizon here at v = 0. So beyond which you come out into an alternate universe through a white hole into a new region. And so because of this, the space-time is not globally hyperbolic. And on the right, I'm just showing the results of our numerical simulations. So that's corresponding to this blue dotted region on the figure on the left. Okay. So now that we have a regular black hole, we want to lift this to a semi-classical theory. So to add Hawking radiation, we take advantage of the conformal trace anomaly. So classically, a conformally coupled matter field has a stress tensor which has 0 trace. But when you quantize it, the trace now becomes non-zero. And it's been shown that this anomalous stress energy tensor behaves like Hawking radiation. And one of the main advantages of working in 2 dimensions is that it's very simple. So this anomalous stress tensor, the trace is just proportional to the curvature, where we introduce this proportionality constant mu to control the strength of the radiation effects. So now if we add this new term to the stress energy tensor for our original equations, we get a semi-classical system that includes black hole evaporation, including back reaction on the spacetime. So we've changed the theory by doing this. We got to make sure that we still have a regular black hole. So rearranging the equations of motion, you get this equation here. It's not really important what any of these terms are, except to note that when this q is 0, the curvature diverges. And for any model that has a singularity classically, unsurprisingly, it's got a singularity in the semi-classical spacetime. But we also find that for non-singular models, for example, Bardeen, there's a critical value of mu above which you get singularities, even when there was no singularity in the classical spacetime. However, we interpret this as just a breakdown of the semi-classical model because it only appears when the radiation scale is much larger than the regularization length scale. And for as long as we're in the weak radiation regime, we have a non-singular well-behaved theory. So here I'm showing some of our numerical simulations. This is a good time to point out one of the limitations of our work, which is that we're limited to quite a small range of parameters, basically only Planck mass size black holes, right? You can see here m equals 1.33 or 0.75. This is units of Planck mass. The numerics just aren't well behaved for larger masses, but nonetheless, we see a lot of interesting behavior, even in this limited regime. First and foremost is to note that the parent horizons in green now come together, meet in finite time, and the black hole disappears, has fully evaporated. Additionally, we find that a white hole are generically formed, so that's this dashed purple region here. Anytime you have a trapping horizon, it eventually leads to an anti-trapping horizon. And as you make the radiation stronger, you can actually get a series of these forming, oscillating in and out. But either way, eventually all of the trapped regions disappear. And at the end, you're left with a space-time which is free of horizons, asymptotically flat, all that good stuff. So I'm showing the now Penrose diagram. So first, let's start on the right, which is the corresponding to those numerical solutions I've shown. So the exact behavior here in this region will depend on what happens to the shell when it hits R = 0. But certainly you can enforce boundary conditions such that it joins to another flat space-time in the interior as the shell expands. And you're left with the space-time, which has the same structure as Minkowski space. So this is in contrast to the standard picture of an evaporating singular black hole shown on the left, where you have a singularity. After the singularity disappears, you get this extra triangle region on top, but the whole space-time is not globally hyperbolic. Also in the middle, this is the quasi-static picture of an evaporating regular black hole. So here it takes infinite time for the black hole to evaporate, and it approaches an extremal state where, again, you have this additional region and the space-time is not globally hyperbolic. Right? So what we found is, in contrast to these, kind of first thoughts, that the space-time actually is globally hyperbolic. And just from that picture, you can kind of see that there's no Cauchy horizon, but we can show this analytically as well. So the affine parameter, solving the geodesic equation, behaves like this: the integral of e to the 2 rho, where e to the 2 rho is the conformal factor. And classically, so that blue dashed line, you can see a ray that originates inside the black hole as it approaches the v equals infinity. That term vanishes, and the affine parameter stays finite. In the semi-classical solution, it goes to infinity, showing that the spacetime is inextensible. And a side effect of this is that it also removes one of the instabilities in regular black holes, which is the blue shift problem. So the blue shift of an outgoing ray is proportional to 1 over the conformal factor. So classically, as a outgoing ray approaches the Cauchy horizon, it blue shifts infinitely, which means that your model is not self-consistent, because implicitly, by working in the semi-classical regime, we're assuming that energies are relatively low. But here we can have energies going to arbitrarily large scales. In contrast, in the semi-classical case, everything stays finite and well-behaved. And in addition, we also looked at one of the other issues with regular black holes, which is mass inflation. So it's been shown that these 2 horizon black holes are very unstable under perturbations. So if you send in an arbitrarily small mass perturbation, it can lead to an arbitrarily large explosion of the energy. So as a simple model, we modeled the mass perturbation as a pair of thin null shells. And the effect of the mass function is given by this equation here, where m is the size of the incoming perturbation, and this term here is evaluated at the point where the shells cross. So you can see below again, in the classical case, this dashed orange line, the term goes to 0, and you get an infinitely large blowing up of the mass function. However, in the semi-classical case, it stays finite, so you remove the instability. So in conclusion, we've shown that we can construct an evaporating regular black hole, which leads to a well-behaved spacetime. So it has no Cauchy horizons, no event horizons, is free of the usual classical instabilities, and basically has no drama, which suggests that the evolution could be unitary. And there's still a lot that remains to be studied about the information in detail, but pending a full theory of quantum gravity, this framework provides a very useful playground for studying the behavior of information in black holes. All right. Thank you for listening, and I welcome any questions. Sorry, I'm having trouble hearing you. The mic does it. I don't think the mic is working at all. Is this plugged in? Can you take this? Uh, yeah, so I've kind of hidden that away for this talk. We've kind of followed basically the same procedure as CGHS. So where the shell comes in, how I've described it is just by glueless regions. It can also be done, right, how CGHS did it, by coupling to matter, and then setting the matter so that it leads to this incoming shock wave, right? So it is basically the same setup as CGHS, but we've changed the action generalizes, so now we can create non-singular models as well. Oh, Okay. Uh, yeah, I'm not sure. I haven't really thought about that. But yeah, I would be very interested to talk to you about that. That's not something I've thought about, but it would be interesting to look at. Right. Oh, good night. Good. Okay.
Thank you. Thank you for having me. So my talk will be based on our paper, which was published in Classical and Quantum Gravity, and we written it with my colleagues Robert Mann, Brayton Howe, Tomasi Hale, and David Budiznia. And before I start, I show you an overview of my talk. So I'll start with revision of higher dimensional black holes. Then I will introduce to you the Disvan-Lunin theory. I will show you that the original BTZ spacetime is actually a solution to this theory. And finally, we can explore some novel solutions to this theory in 3 dimensions in a nonlinear dynamic setup, nonlinear electrodynamics. Okay, so let's start with black holes in higher dimensions, and I will show you this table, which you all know. So we have different types of black holes. The easiest one is the Schwarzschild black hole, which is a massive static black hole. You can add electric charge to it, and you obtain Reisner-Nordström spacetime, and those two can be easily generalized to higher dimensions as Tanglini spacetimes. Then you can have massive and rotating black hole. This is scarce spacetime. It can be generalized to Myers-Perry black hole. And in 4 dimensions, you can have black hole, which is massive, rotating, and electrically charged, Kerr-Newman spacetime. And to go from Kerr to Kerr-Newman, it is really straightforward. But if you want to generalize it into higher dimensions, it is actually very hard because we don't have the counterpart in higher dimensions for Kerr-Newman. And people tried lots of other things, like, for example, modifying the action by adding some topological Chern-Simon stem, or which looks like this. But for general coupling constant lambda, it does not yield analytic solutions. So this attempt wasn't actually much successful. But now we have a solution, let's say, and that's Van-Lunin theory. So if you are interested, you can find all details in the paper. So this one and Lunin also try to solve this problem by modifying the action by adding a topological term with a dimensionless coupling, lambda. So here you can see the action. The first term is the standard Einstein-Hilbert with Ricci scalar, cosmological constant, and the Lagrangian for electromagnetic field. And then you can see the topological term, which contain field A, which is the electric potential. But also there are two other new fields, H and K, which will be non-dynamical. They won't appear in thermodynamics of black holes. And for that fields, we have some constraints which must be satisfied. So as you can see, A is a potential for standard electromagnetic field strength F, And also there are potential B and C, and if you take their exterior derivative, you obtain those H and K, which are in the topological term. This theory, also there are two algebraic constraints. So your wedge product with F and H and K must be equal to 0. So this must be satisfied. And then this theory gives you a solution, gives you charged and rotating black holes in all odd dimensions. And because the new term is topological, it doesn't modify your energy momentum tensor. So your Einstein equations are still the same. What is modified though is your Maxwell equation or your equations of motion for electromagnetic field, because instead of 0 on the right hand side, you can see you pick up a current which can be calculated from those H and K. So you have a little bit modified equations of motion for electromagnetic field. So keep this in mind, and now let's digress a bit and let's talk about the BTZ black hole spacetime. So the original BTZ black hole spacetime was found in 1992 by Ramon and Zanelli. That is why it's nicknamed BTZ. And is a three-dimensional black hole which is rotating, and it can possibly be also electrically charged in a spacetime with a negative cosmological constant. And the solution looks like this. So as you can see, we have two different metric functions f and h, which contain mass parameter m, electric charge q, rotational parameter j, ADS radius l, and also that are shown in the logarithms just to make sure that those logarithms are dimensionless. And as you can see, the charge is supported by a static-like potential A, because we have rotating black holes, so we would expect that A will have dp and dphi components, but here we can see it has only dp component, so it is quite interesting. And this is the solution to Einstein equations, but it was pointed out that it actually doesn't satisfy vacuum Maxwell equations. So this theory or this space-time was considered to be incorrect, of course. And in 1996, people found a correct version for 3D rotating and charged black hole. But even if this is not the solution to standard Einstein-Maxwell theory, it is actually a solution to the Desvandt-Lulin theory, which I showed you a moment ago. And it is a solution provided that we have choose this potentials B and C, which will give you those H and K. Just to remind you, this is our Desvandt-Lulin theory. So you can see that if you choose B and C to be like this, you can calculate fields H and K and the current of the right hand side of the equations of motion. And considering this, your original BTZ spacetime is a solution to Desvandt-Lulin theory in 3 dimensions. And it's not all. It is actually, or it actually satisfies equations of force-free electrodynamics. So the first thing which must be satisfied is that your electromagnetic tensor must be degenerate, which is equivalent to the condition that your P invariant must be equal to 0, which is true for original BTZ spacetime. Then if you write down your integrability condition and your equations of motion, you actually come to the equation on the right, which is an equation characteristic for force-free electrodynamics. And if you calculate your S invariant, you'll find out that this force-free electrodynamics is electrically dominating. And you can also do thermodynamics consistently, because your first law of thermodynamics and smart relations are satisfied. And as you can see, there are no charges or no quantities which would be related to those new fields in the topological term. And here you can see the thermodynamics. So this was original BTZ spacetime. And now we can try to find some new solutions to this theory. And let's say in 3 dimensions. So again, we can see the action and we can see here's the Lagrangian for the electromagnetic field, and we use standard Maxwell Lagrangian for the BTZ. But now we can try to replace it with Lagrangian of some nonlinear electrodynamics. So instead of Maxwell Lagrangian, let's take some arbitrary function of our invariant S. Then instead of standard electromagnetic tensor, which would look like this, in Maxwell case, we will use this d mu nu, which will be relevant. Then instead of this energy momentum tensor, you obtain energy momentum from electrodynamics, which looks like this. And finally, the equations of motion will have the same structure, but you will replace at mu nu d mu nu. So let's try to take this nonlinear electrodynamic setup. Let's have those B and C or H and K the same as before. And let's try to find the solutions to the Hausmann theory for general nonlinear electrodynamics. So if you do that, you'll find out that your solutions will have this form. So you can see that the metric has actually the same form as the BTZ with metric functions f and h. H has always the same form, and f has the part which is common for all the solutions, and f tilde is the part which is dependent of your specific choice of NLE. And then your electric potential will always be static line, where phi 0 is electrostatic potential dependent on your choice of NLE. So then you'll find out that all those solutions for NLE also satisfy equations of force-free electrodynamics because their electromagnetic tensor will be degenerate, and their integrability condition and equations of motion yield the equations of force-free electrodynamics. And you can also do thermodynamics as before. These are the first law and the small relations which must be satisfied, and the ellipse stands for some additional terms which can appear there, because when you take some NLE, you will probably have there some coupling constants. You can treat them as free variables, and you can vary with respect to them and obtain additional terms to your thermodynamics. And your thermodynamic quantities will look like this. So some of them depend on your specific choice of NLE, some of them don't. And just to be specific, I can show you some concrete particular example, which is regularized conformal electrodynamics given by this Lagrange. So we can see two different coupling constants here, alpha and beta. Beta actually tells you something about the coupling between gravitational and electromagnetic field, and alpha is connected to the regularization, because you know that when you have some theory of electrodynamics, it usually diverges at the origin and you want to regularize it. So instead of your potential being something like minus E over R, you want to get something like minus E over R plus something, where that something depends on that alpha. So if you send alpha to infinity, you obtain standard conformal electrodynamics. So this is your Lagrangian, and if you use that, those are metric functions and electric potential which you obtain. And finally, this is the thermodynamics. As you can see, we can vary with respect to alpha and beta to obtain two additional terms in the thermodynamic laws. And these are our thermodynamic quantities. As you can see, apart from standard thermodynamic charges, we also have pi alpha and pi beta, which are potentials connected to alpha and beta. So that was an example, and this brings me to the end of my talk. So I showed you that the Hausmann theory is a theory which generates analytic solutions for charged and rotating black holes in all odd dimensions. I showed you that the original BTZ spacetime is actually a solution to this theory in 3 dimensions. I also showed you that we can construct some novel solution to this theory by replacing standard Maxwell Lagrangian with some nonlinear electrodynamics, and all those solutions satisfy equations of force-free electrodynamics. So that's all from me. Thank you for your attention. Thank you. You mean like if there are some other solutions in three dimensions for Maxwell? Yeah, those generalizations are given there. Okay. I need to click that. So yeah, this is the general form of nonlinear electrodynamic solutions in three dimensions, provided that you use the same fields H and K, which were used for BTZ. Like, sorry. Well, the Sandonian theory just contained them, so I don't know if we have some other solutions to that.
What would be a physical way to interpret this additional topological term that you mentioned that was defined in Is
It's an interesting question, but I'm not sure about the physical interpretation. Like,
Thank you. So this is the time to hear
So I still have to use that, all right? That is better in my case. Okay. And how do I click where yes with it, right? Can you hear? Yes. Well, thank you very much. As you said, my name is Jose. I'm a postdoc at the University of Burgos, Spain, and I'm going to present a joint collaboration with Luis Garay from Complutense, and also some students, Alejandro Blanco and Josep Tormo, that have been doing their master thesis on these topics. So I just want to tell you that this talk is more like an invitation to read this paper rather than a technical explanation, because I only have 15 minutes, I think. So just as an introduction, this is a detector models talk. If you think about it, whenever you read papers about detector models, you realize that the common theme is that there is a fundamental object in there. There is the scattering operator in one way or another, that it is a time order exponential of some integral of some Hamiltonian weight that commonly takes the form of a multiple coupling of a set of independent detectors that couple through some operator J with the same quantum field amplitude. So usually the things that one can calculate in this setup come from two paradigms. One is to say that the dynamics implements some reduced dynamics over the state of the detector, and that's basically doing a partial trace over the field. And then there's the somewhat dual notion of that. There is that I want to know what it means, what I'm measuring about the field once I measure the detector after the interaction. And well, basically that's the concept that Chris
cluster developed in detail yesterday in his talk, right? So, well, I will cite this little work that we have Maria Papayoriu and Eduardo Martín Martínez, from which we concluded that in this formal in the sense that well, it's not very well, we were not very careful with the mathematics, but basically the idea is that whenever you have this kind of detector models, if you want to preserve the covariance of the results and also the causal structure, the detector has to satisfy one of these three requirements. That is, the detector is also a quantum field. Either, well, the detector may not have internal dynamics. That's something the people use a lot, in the sense that the free dynamics of the detector are trivial. Or rather, the most common thing that we can find in the, say, unreviewed literature is that the detectors, whatever detector you have, only interacts with the field through a time-lag trajectory, although, as we will see, that has some technical problems and requires some renormalization scheme, right? So, if we want to discuss causal behavior of these models, we really need to understand how the detector couples for a finite amount of time with the field, right? So in this case, what is more natural is to consider that the channel acting over the state of the detectors is a perturbative series in some coupling constant, and then the dynamics can be implemented locally in the sense that the dynamics can be calculated. So in this case, even if the interaction Hamiltonian doesn't fulfill all the requirements that we had before, then there are some observables like excitation probabilities and the kind that are well defined and are causal at all for low orders in perturbation theory. And therefore they admit these are, let's say, covariant and causal observables. However, these observables in perturbation theory are never bounded operators. So if we want a measurement theory, which we want gets finite dimensional, so one gets one operator that describes probabilities for any state, then we cannot use perturbation theory. On the other hand, there's a different tradition, let's say, in the context of what I'm calling the detector models, that is exactly solvable models. These are based on the idea that the Heisenberg equations of motion are linear. That is, if our detector is a harmonic oscillator, for instance, then the whole system, the joint system of field plus detector, admits a formal solution in terms of Green's functions. That is, we're not resorting in principle to Dyson series. And what we have there is that we say that the Heisenberg evolution of the oscillator is a homogeneous part that only acts over the detector, the degrees of freedom, times a part that only depends on the field's degrees of freedom. So solving these kind of systems at the non-perturbative level requires to solve overall an integral differential equation. So what has been done traditionally in the literature is to resort to Laplace transform analysis because it's the most natural thing to do when one has a stationary situation, for instance, an inertial detector or a uniformly accelerated detector interacting with a vacuum. However, these Laplace transform methods do not work for local interactions, so they don't apply there. And also, one can imagine that they don't apply for non-stationary spacetimes. Also, something that we kind of did also with Maria, with Professor Harris and Astopoulos, was to try to see what were the used observables in the case of this situation. And we saw that indeed, since that there is a problem with induced observables in this regime, because one basically, when one solves this equation, one is imposing initial conditions, which naturally involves this continuous function. So if we have the following wish list, we want a model that is local in the sense that it doesn't have UV cutoffs nor everlasting interactions. that the equations of motion are linear in such a way that we don't have to resort to Dyson expansions. That is covariant and causal. That is, we don't want extended and non-relativistic systems. And tractable. That is, we want to solve a finite set of differential equations rather than a general partial differential equation, which may be very complicated. That excludes field-field couplings. Then we propose the following type of model. Don't get scared. This is just a harmonic oscillator that couples in proper time to the field amplitude along a word line. And the interaction is moderated by a time window or switching function chi. And on the other hand, we have a general field in a globally hyperbolic spacetime that couples through the following covariant current to the harmonic oscillator in proper parameterized in its proper time. So this is just a generalization of the system that we have down there. That is the kind of system that one solves with Laplace transforms, and that the literature is known as quantum Brownian motion, in the sense that one can try to model that field amplitude that is there, evaluated at a single point in spacetime, as some path of harmonic oscillators. How much time do I have? 15 minutes so far. Okay. So I'm just going to discuss the results, the kind of things that we found analyzing this system. First, the dynamics is ill-defined because we're taking a point-like limit, and that's something that you cannot get rid of. However, there is a way of renormalizing distributions that have a more covariant flavor, in the sense that there is a mathematical abstract renormalization procedure, which is based on the so-called Efter-Glasser renormalization. And we see that in this kind of linear system, the only thing that you have to renormalize the theory at all orders are the so-called advanced and retarded solutions of the equation of motion when evaluated along a single word line. After the interaction, the Heisenberg picture operators associated with the detectors, that is, the scattered operators, are well defined in any Hadamard representation, even though they're defined over word lines. And they take a relatively simple form because, the solutions to the integral differential equations that show up are one-dimensional, and one can basically understand them in terms of some enveloping waves that create dissipation plus some oscillatory terms. The induced observable associated with space-like separated detector, when one has more than one detector, are localizable in space-like separation, which is not surprising. But moreover, they're bounded in norm by the initial norm of the. So they're, in a way, the map that takes the induced observable is norm decreasing, something that can be shown in more general terms. But in our case, we have a very clear estimates of how the norms behave. And a couple of things of cherry on the cake. So it turns out that there's a nice relationship with the so-called Huygens principle, that is that solutions travel along line-like geodesics and Markovianity in this type of systems. So it turns out that when you have one of these detectors, not two, or several of them in space-like separation, any interaction of the field, because the detector is point-like, any interaction of the detector with the field dissipates away, cannot come back. So there's no backflow on formation. So then we have an open system that the non-perturbative level, without any approximation, is Markovian, which is not something we can understand within non-relativistic physics. An application of or analysis of this type of systems comes from also we have the motivation that at the perturbative level you cannot actually talk about detecting non-Gaussianities with detectors that is at the lowest order with this kind of models. So what we did was to analyze what happens with these detectors at the non-perturbative level when they interact with a non-Gaussian state of the field. And we saw that all the cumulants of the detector after the interaction are associated with cumulants of some distinguished field amplitude in the initial state of the field before the interaction. And with that, I think we have plenty of time for questions. I have more slides if you have more technical questions. And I would like to thank you for coming. Great.
Conditions. So I'd like to better understand what causality it means, like sorting type problem.
Yeah, we were
Exactly. Explanation of what's that. It's okay.
yeah, well, we were in that work with Maria Papayorio and Eduardo. We were thinking about the sorting type problems. But well, basically the intuition is that the whole dynamics is microcausal in a way. So there's no anything that you can do with the dynamics in that framework that the say doesn't respect the partial order structure that you have in the background in that case. The problem is that when you do it in a point-like limit, you get divergences because yes, the theory is telling you that that's not a nice thing to do. Say it again, please. I'm sorry, I'm not understanding. Like, I cannot hear. Okay. Sorry. I mean, and at least not for this purpose. Okay. So what I meant is that yeah, I know that it could be controversial. I mean, I don't have anything against the using quantum fields for as probes, nothing at all. So the thing is that once you look at the equations of motion of a linear couplet with the two quantum fields, and you try to put there a potential, it seems that there to get the solution, you really need to calculate the solution of a partial differential equation at all orders, right? So okay, you can have perturbative schemes that like you did in your paper with this I think is born series or I don't remember, and of course that's okay and that respects locality etc. But I mean, so I thought that maybe this alternative route could give you in some situations easier results that convey more or less the same information. It's just like at the level of the differential equations we get. I mean, in some cases we even get just a damped harmonic oscillator. There is no abstraction beyond technical.
Say again. Here.
Go to the right.
What is?
Yes.
Okay. So next up we have Latinas who will tell us about what some of the foundations teaches us about Latinas.
Thank you, Vilasini, for the nice introduction. And thank you all for being here. So today I want to tell you why quantum foundations are actually important for studying the black hole information paradox. And I will do this by showing you two kinds of thought experiments, one involving a black hole and one that is very famous in quantum foundations, and show you that they're actually closely related. So let's start with the black hole thought experiments. And it is actually a puzzle. In both fields, there are lots of puzzles. And what puzzles come out to more technically is usually no-go theorems, which means you have a set of premises, and those will turn out to form a contradiction. So if in the following I make some assumption or premise that you don't agree with, then don't worry, this is precisely the point. It's a point to show that these premises don't, they're not consistent anyway. But often there is disagreement which premise is the right one. That's why these no-go theorems are interesting, even if for you it's clear which one is the wrong one. So the puzzle I'm presenting is based on the puzzle or the protocol presented by Haydn and Fresco. And let's start with it. So how does it usually start? So you have an observer, which is conventionally called Bob, who prepares some shell of matter into a state such that it will collapse into a black hole. And he does this, and he will, in the end or in the start, prepare it in a pure state. So this will be important for the derivations later. And then what does he do? So once it has formed a black hole, which here I drew kind of pictorially as a spatial slice because it's easier to then move to the more abstract part, he built some detector around the black hole. And this is not a kind of conventional detector where you measure the Hawking radiation that is coming off the black hole. What it's doing is taking this Hawking radiation and feeding it into some quantum computer. So here, this is my very abstract depiction of a dilution fridge. Feeding it in there. So no measurement is actually done. It's just somehow collecting it and storing it in a way that is very nicely accessible for the observer, Bob. And then what does he want to do? So he waits some time, and he actually, in this thought experiment, he waits until the page time. And if you don't know what this is, for the purpose of this experiment, Bob models the black hole as some actually finite dimensional quantum system, and he will just wait until the dimension. That is not intended. Okay. Let's hope my laptop doesn't lock again. So he will wait until kind of the dimension of the Hilbert space he associated to the black hole will be only half as much as it was when it started. And at that point, he will employ his more brave friend, Alice, who he gives one half of an entangled pair, which he prepares beforehand, and tells her, because she's more brave, to actually fall into the black hole and take it with her. And he also gives her some instructions on what she should do there. But we will come to what Alice should do in the black hole in a later step. Okay, so what does Bob keep doing? Once he said goodbye to Alice and she's merged with the black hole, it just keeps on collecting the Hawking radiation. But actually, in this experiment, Bob is very indecisive. He doesn't get away that well. He wants to actually recover the spin S1, which has jumped into the black, or fallen into the black hole with Alice. And now he can think or analyze the situation and ask, okay, can he do this? And the kind of premise this entire experiment is based on is that the black hole and the Hawking radiation process is all some unitary acting on here the entire shell of matter and, well, the quantum computer that's collecting it. And this unitary should be typical, which makes quantum information theorists very happy because they can say a lot of things about typical unitaries. And also the later radiation process. So once Alice has fallen in and he collected some more radiation. So here I denoted the early radiation, as it's usually called, by R, and the later radiation by R prime. So later, in the end, he has both R and R prime stored in his quantum computer. And the entire setup can be abstractly written as some quantum circuit, in case that, to make the situation clear, like what is acting on what. So now Bob would like to figure out if he can apply some unitary onto the quantum computer, which harbors the radiation R prime, and actually recover the spin R1. And when you assume that these unitaries are typical, you can use very powerful quantum information tools called decoupling theorems, from which it immediately follows that there is actually such a unitary only after when R prime is only actually a few qubits, such that he can recover some spin here, also called S1, which is again maximally entangled with S2. Okay, so Bob is happy because he recovered his spin S1 in the end. And let's see what happens to Alice and what Bob told Alice to do. Well, Alice has just fallen into the black hole. And if you assume that the black hole is actually very large, then for Alice, when she's fallen over the horizon, nothing really happens. The curvature is still very small. And what Bob can tell Alice to do is to say, okay, please just measure S1 once you're in the black hole. And, well, you cannot tell me the result anymore, but just use quantum theory. And, well, Alice does this, as she's still Bob's friend. And when she got result 0, she can then apply quantum theory and, well, apply the usual rules you find, for example, in Nielsen-Schwang. And there she would say, okay, I've measured result 0, so S2 should be in state 0. But now we can compare their two conclusions they came to. Well, what do we see? Alice would say, okay, I've seen state 0, so S2 is in state 0. Whereas Bob would say, okay, no, this is not actually the case. I could recover something from my Hawking radiation, so S2 is actually entangled with S1. And if you go through this experiment in the space-time, you can actually find that these two views can exist on the same Cauchy slice. So there's the same Cauchy slice where Alice holds this view perspective onto the experiment, and Bob holds this perspective. So if we now kind of add the premise to the mix, which said that any observer, no matter if they're in black holes or in other weird situations they find themselves in, their states they assign to systems should be compatible, then we've run into a problem. And now we can formalize what I actually announced before. We can make this into a no-go theorem. So we can say, okay, the following premises are incompatible. So we can say, okay, quantum theory is universal. So here I used it actually, I want to stress this in two different ways. So we said quantum theory is universal in that it can be applied to even strange objects like black holes. So that's also universal in the sense that even if you are falling into a black hole, that you can still apply it. Then this is the last premise that we use, is that basically we want states of different observers to be compatible. And we use various gravity assumptions. So I didn't list them here all, but the ones I explicitly mentioned were, for example, that there's a smooth horizon or there's no drama, as some speaker before me named it, that, for example, the black hole is actually a finite dimensional system, and it evolves according to a typical unitary and not some unitary with very special features. Okay, so now that we've arrived at this no-go theorem, we can ask ourselves, can we actually make this puzzle more abstract? So let's try to do this. And let's remind ourselves of the last picture we had of Bob. What was the essential feature there? We had one observer. With one observer, Alice, who was actually falling into Bob's very fancy detector. And for him, Bob, this region here, then continued to evolve unitarily. Well, if you come from quantum foundations, you have your kind of favorite tool, which is to say we can put observers in isolated laboratories. So let's do this. So here I just say, okay, Bob applies quantum theory to whatever Alice is interacting to, or he is very fancy, as he could before. So he could also put this very fancy detector around Alice's lab, and she would be kind of none the wiser, because this detector must have been very large before, if he could put it around the black hole and collect whatever thermal radiation or other stray products are coming off of Alice's lab when she's performing her experiments. So for Bob, all of this here should be evolving unitarily. So now we can again look what is Alice doing in her lab. Well, she is just in this in her laboratory, and what she does is that she measures her qubit S1, and she again measures it in the computational basis. She will get some result, and she likes quantum theory. She again applies the update rule and sees, okay, S2 is in state 0. So now we can again come to the same slide as before and say, okay, let's compare their two perspectives. Well, we have Alice, who just is inside this isolated lab and applies quantum theory to her side of the perspective. And Bob, who is outside the isolated laboratory, would say, okay, this entire thing has evolved unitarily. So in particular, I could again apply some recovery operation and recover the some spin that is maximally entangled with S2. So they again have run into the same disagreement as we had in the previous slides with the black holes. But now let's look at the no-go theorem that is coming out of this. So, yeah, I forgot to mention this. So everyone that knows quantum foundations probably or knows the Wigner's friend paradox already was thinking in their head what this was going to. This is some version of Wigner's friend paradox that we've run into, and this is kind of the class of quantum foundations experiments that I want to argue are close to black hole experiments. So let's look at the no-go theorem that has come in, or what kind of premises did we use? We didn't need to use any of these gravity assumptions. We actually only needed to use the first two. We needed to use that the quantum theory is universal, and we needed to use that two observers, no matter if they're in weird situations, like in isolated laboratories of their colleagues, they can still apply quantum theory, and they can still apply quantum theory, and they should still have compatible states. So also these two assumptions just alone leads to a no-go theorem. So we can kind of delete the other two assumptions. So what does this tell us? Actually, the gravity no-go theorem is, in this sense, logically kind of strictly weaker than this one. So if we want to make statements, are these gravity assumptions actually incompatible? We need to make sure that we're not using some assumption which we already know to be problematic with the universality of quantum theory. Okay, so now that we've applied it to this situation, so what can we generally learn from this? So first thing I want you to take away is basically, look, there's kind of a correspondence. If you have some observer, you throw into the black hole and you ask yourself, what is her experience? And what is the experience, or how does the outside observer describe this situation? Then what you're doing is, in essence, some kind of Wigner's friend experiment. So you need to be careful that any assumptions you're using are actually not already known to be incompatible with quantum theory in these kind of contexts or in general. And recently, there's been quite some progress on what kind of assumptions are incompatible, and it's surprising how far you can go. So even mild assumptions, like if I know that Villasini knows some measurement outcome, then I also know that measurement outcome is actually incompatible with the universality of quantum theory. So what we then did is went into the literature and saw what kind of paradoxes are there that are implicitly using the assumption. And one of them, for example, is the firewall paradox, which also uses this assumption I just made the example with Villasini. So with this, I would like to thank you, and I'm looking forward to your question.
For the interesting presentation. Maybe I'll start with the question. If you could go back to the previous slide where you compared them.
Yeah.
So your interesting premise is that there's a correspondence between these two classes of paradoxes.
Yes.
There, of course, there's a lot of work on the Wigner's friend paradox.
Yes.
In particular, in that case, there are many complete resolutions that have been proposed.
Yes.
Which also refine these assumptions.
Yes.
To further ones. And in particular, one viewpoint there would be that, in fact, the universality of quantum theory is not the thing necessarily the issue, but how you use quantum theory in these experiments. In particular, one resolution that's been proposed would be to say that you should not use quantum theory across different Heisenberg cuts while exploring.
So
I would be curious to see, like, in that sense,
yes, so
exist very concrete resolutions for one side, and then you mean
yes, so there is actually a correspondence between resolutions, not in this case, but in the like more simple Wigner's friend case. So the kind of resolution to these Haydn-Preskel type puzzles is usually called black hole complementarity, which means basically you shouldn't compare what Alice says about the inside with what Bob says on the outside, because what I didn't say here is that Bob cannot actually meet Alice anymore. So Bob is too late to meet Alice. So the premise is basically if two observers will not meet anymore, the way they apply quantum theory shouldn't be they can whatever they think about the state, we don't care. And this is similar to kind of an epistemic interpretation of quantum theory in Wigner's friend scenarios, where say, okay, Alice has her opinion about what the state of the system in her lab is, and Bob has his opinion about what the state of the system in his lab is. And those are opinions, but those are both fine.
Thanks for your answer. Maybe we should discuss this.
Yes, we'll discuss this more later.
It's just about fringe resolutions.
Yeah, we can discuss this in the break.
Let's discuss it then. You have any more questions from you?
I wouldn't say it's no different. I would just say the same issues that arise there, that you have perspectives of two different observers, one which is in a system which is evolving unitarily, is also applicable there. And you should look, are you actually making assumptions, or are you basing your argument on premises which are known to be problematic there? And then try to make arguments which lead to problems there, maybe. I'm not saying that these assumptions you make in gravity are compatible, but I'm just saying the arguments that are made now are based on assumptions which we know to be problematic, and we should take care of this.
Yeah, well, quantum patterns.
Sorry?
Wow.
So, yes. So in Wigner's friend paradox, these gravity assumptions are not relevant because you don't put in gravity. They're just to say these two assumptions are already incompatible on their own. You don't need that. So usually these calculations in GR are also made that Alice is infinitely light. So Alice doesn't have any matter. So if you have matter, I haven't done these calculations myself, she at some point should merge. Or another way to say it is like these protocols are usually not adversarial. So you can just say, look, Alice promises Bob that she will fall in. So he could plot this world line on like a Penrose diagram. Yes. I mean, this is one of the assumptions that is made, that the horizon is smooth and that
No.
yes, you're allowed to do this. It's a no-go theorem after all. Yes, you can question the assumption that basically the state update rule needs to have some additional structure when you put it in space-time. That's totally valid. That's why it's a no-go theorem. So basically, you can question the assumption that kind of the normal state update rule, as you find it in Nielsen and Schwang, for example, if you consider it in space-time or stuff is space-like separate, that this should be different. But this is precisely the point. We have assumptions which are incompatible, so you can question anyone you like. Wait, can you repeat the statement? In some sense, the measurement problem is relevant here, yes. Yes, sorry.
Everybody forgets. Like yesterday?
Sorry?
Like yesterday? You put the mic in your line?
Yeah.
So, what's happening now?
I don't know. It's doesn't know.
Yeah.
Maybe it's the wrong. Yeah, it looks like this one is not.
Yeah. This one? Maybe.
I'm sure which they were all on the floor when I got this one.
No, it's not reading it. No, not to Today,
Oh, one of them. Yeah. Mhm. I think so. Okay.
So for the last talk before the coffee break, we have Liška, and he will be talking about black hole thermodynamic probes, thermodynamics probes, influence principle.
Good afternoon. Thank you so much for the introduction. And I'm going to talk about a short essay we wrote together with Ana Alonso Serrano and Luis Garay. The idea of this essay is very simple, and I should say it's mostly rooted in classical physics. Nevertheless, the quantum part will come at the very end as possible future projects. And here I just want to sort of show you the proof of concept and some basic framework. So the motivation for this work comes really from the usefulness of the equivalence principle for gravitational theories and potentially for quantum gravity, at least the way I see it. In its basis, equivalence principle is a very simple statement. You take some test physics and you make a claim that this test physics is not affected by the presence of the background gravitational fields. That is, you can always, for any gravitational field where you do the experiment, you can find a reference frame in flat spacetime where the experiment yields the same result. And actually, this sounds simple, but the trick is in the phrase test physics, because that is very difficult to define. And actually,
by the different definitions of admissible test physics that you can take, you have many different statements of the equivalence principles, as you probably know. And these statements of the equivalence principle in turn actually allow you to classify the various models for gravity that you may consider, both classical and quantum. Basically, there is one main difference in how different equivalence principles go about it. There are the equivalence principles for whom the test physics is just non-gravitational phenomena, electromagnetic radiation, moving of particles along force-free trajectories, and so on. And in this case, these equivalence principles constrain the kinematics of the space-time in your theory of gravity, essentially constraining it to being locally Lorentz invariant. Then another degree of this is considering statements of the equivalence principle that deal also with test gravitational physics. And in this case, it turns out that they already impose fairly stringent constraints even on the gravitational dynamics that is compatible with them. And this is the case that I'm going to talk about more in the following. Here is a short list of papers dealing with the equivalence principles in recent years. So you can see that this is still an active field, both in the philosophy of physics community and also in more mathematical works. So the particle equivalence principle I'm going to talk about is the most stringent one, the so-called strong equivalence principle. And for this principle, the test physics is any fundamental physical experiment with negligible back reaction on the space-time. That means any normal experiments that you would consider, the experiments done in LHC, any experiments with electromagnetic radiation, as long as they are local and do not create their own strong gravitational field. But also one thing that must be included are gravitational test physics phenomena. For example, motion of test particles with non-negligible self-gravity, including small black holes, neutron stars, and so on, or the propagation of gravitational wave, if you treat it as a small perturbation on a fixed background whose back reaction can be neglected. And actually, the strong equivalence principle can be shown to be equivalent to two statements. One of them is that the physics that you consider is locally Lorentz invariant, and that must include the gravitational phenomena. So in particular, gravitational wave propagation must respect local Lorentz invariance. The other one is that self-gravitating test bodies, or also non-self-gravitating test bodies, must move along geodesics in the space-time. And if you have these two assumptions, then the strong equivalence principle does work, but this turns out to be very restrictive for your gravitational dynamics. Essentially, only general relativity and unimodal gravity are known to be compatible with all these assumptions. But the problem is it becomes fairly difficult to look for violations for generic gravitational theories, especially given the number of alternative models that you can imagine. So this is not an exclusive statement, this is just the theories that we have so far in some way explicitly checked. And that is where I think black hole thermodynamics sort of comes in as a way to offer a very quick and simple test for violations of the strong equivalence principle. Essentially, only thing you will need for that is the equation for Volt entropy, and you can proceed with that. And there is a precedent for considering the relation between thermodynamics and equivalence principles. First of all, the weak equivalence principle, which basically states that particles on which no other force but gravity acts move along geodesics. This one gives you the geodesic structure for the space-time, and as a consequence, it implies, for example, the Tolman law for the scaling of temperature in equilibrium system in gravitational field. Similarly, the Einstein equivalence principle that concerns arbitrary non-gravitational test physics, that one essentially enforces local Lorentz invariance of your theory, and that more or less directly through Bizonianov-Wichmann theorem gives you the Unruh effect even in curved spacetimes, at least locally. So there is some tradition for connecting thermodynamics and equivalence principle, and the thing we focused on was black hole entropy and its connection with strong equivalence principle. And in this case, there is a sort of folklore statement that you can find in several papers, and that is that strong equivalence principle directly proportional to the area of the horizon. That would make sense since we know strong equivalence principle to be kind of compatible with general relativity, but not with most other theories. So it's a good guess to take the entropy that you get in GR as the only compatible one. However, it has never been systematically analyzed. And the problem also is we cannot directly measure entropy, and any equivalence principle is phrased strictly in terms of measurements. So it is even questionable whether you can consider experimental violation of this strong equivalence principle based just on the entropy formula. So for this reason, we devised a local thought experiment that considers fall of matter into a small Schwarzschild black hole that we use as our test arena for the equivalence principle. And in this case, the particulars of the idea are we have to have a static spherically symmetric black hole. There is probably no problem with generalizing this to rotating black holes or charged black holes or anything. We just went for the simplest case. And around this black hole, we have to assume an empty region of some radius L much bigger than the radius of the black hole itself. The reason is that otherwise the black hole's effect on the matter fields in its vicinity would become significant over time, and it would lead to a significant big reaction. With a vacuum region around the black hole, this is present. So we actually assume a scale hierarchy of R plus being much smaller than L, and that in turn must be much smaller than the local curvature length scale. Otherwise, of course, the black hole is not a negligible perturbation for the space-time, but it becomes something that will have significant back reaction on the curvature by itself. And with this in place, we can guarantee that the background curvature will not affect the black hole geometry, that it will be really a Schwarzschild solution, typically. And with this setup, we prepare some matter that is fully randomized. It is only heat, it cannot perform any work. Let's say we take some thermal gas in a small container. We prepare it in the faraway region from the black hole, and we slowly, carefully lower it inside so that no work is being done. And in that case, the physical process first law basically guarantees that the heat absorbed by the black hole is equal to Hawking temperature times the change of black hole's Volt entropy. And taking the ratio of this change of Volt entropy with temperature and heat term, we will find that this ratio is a dimensionless quantity, which, if it does depend on where in the spacetime we constructed a black hole, on the background curvature of the spacetime or on any background properties of it, it does violate the strong equivalence principle, because then we can take the values of this number as in different points and use them to distinguish them apart. In other words, you can make a local experiment of measuring this S in two different spacetime points, and you will not be able to reproduce the result in flat background spacetime. So with this thought experiment in place, the only thing that remains to be done is to apply it to various theories and see what we get. So the first completely unsurprising case is general relativity, for which the ratio S is just 1/4 from the famous Bekenstein entropy being area of the horizon over 4. And in this case, the strong equivalence principle is not violated, as we would expect. The other one is f of r gravity, for which we get, for the ratio S, that is the derivative of the function f with respect to r over 4 in that point, and because this does depend on the background curvature, it violates the strong equivalence principle. Again, nothing to be surprised about. F of r gravity is known to violate the strong equivalence principle. The same result will apply to quadratic gravity and basically to any theory that has higher order curvature terms with dimensional full couplings. A particular case of this is the Lovelock theories of gravity, for which it gets a little more interesting. As you can see, the ratio S does depend on the background curvature through this tensor P, which is just the derivative of the Lagrangian, of the Lovelock Lagrangian with respect to Riemann tensor, which for any Lovelock theory but GR is going to be dependent on the background curvature. But the interesting thing is that in Lovelock theories, it was shown that self-gravitating test bodies do follow geodesics in background spacetime. It was done by Stefano Liberati and collaborators some 10 years ago. Therefore, the implication of this is that for Lovelock gravity, the local Lorentz invariance of gravitational physics must be violated, because otherwise the strong equivalence principle would have to go through. And it turns out that this is indeed suggested by the study of gravitational waves in Lovelock spacetimes, where it seems that they do not generically propagate with the speed of light, and there is even possibility of superluminal propagation, suggesting indeed local Lorentz violations. And the last case we considered from these simple ones that you can do very quickly was entropy as an arbitrary function of horizon area. This is something that appears a lot for alternative entropy prescriptions. For example, Barrow entropy that considers a black hole horizon to have a fractal structure has this kind of entropy scaling with area that is non-trivial. The same applies to Tsallis entropy and to Kaniadakis entropy and other proposals. And in this case, the entropy turns out to, or the ratio S turns out to depend on the area of the horizon in a non-trivial way. But since this is an intrinsic property of our black hole, not affected significantly by background curvature correction, it actually does not violate the strong equivalence principle. To be fair, this is a statement about these non-standard entropy prescriptions. We do not know whether they imply any modifications to gravitational dynamics, much less which exactly, even though there are some talks about it, like which gravity theory can give rise to this type of entropy functions. But in either case, here we see a potential entropy prescription that can be compatible with strong equivalence principle without being simply proportional to the horizon area. And there would be other prescription like this, for example, relying on extrinsic curvature of the horizon or other quantities intrinsic to it. So, lastly, a few concluding remarks. The main selling point of this test of the strong equivalence principle is its remarkable simplicity. You can do it very easily, just the moment you have an entropy prescription available, which usually tends to be the first thing, one of the first things that is derived when someone considers a new gravitational theory. And as we've seen on the example of Lovelock gravity, it can yield some novel information about the structure of the theories relatively easily. For example, if the gravitation, self-gravitating bodies move along geodesics, you have to look for violations of Lorentz invariance in gravitational waves and so on. As for the possible outlook in the future, of course, it would be very interesting to apply this in semi-classical and quantum setting. And one of my hopes is that it might help to clarify the statement of strong equivalence principle in quantum physics, which there are statements of weak equivalence principle, Einstein equivalence principle, but to my best knowledge, the strong equivalence principle is still missing. Could be interesting, for example, in the framework of quantum difference frames. Another interesting question is the strong equivalence principle in semi-classical gravity, where it's neither clear how to properly phrase it, nor whether it is obeyed. And of course, the next related question is ADS-CFT correspondence, in which the situation is roughly the same. So that is all from me. I thank you for lasting this long and thanks for your attention. Yeah, I wrote the wrong one in the presentation. I'm sorry.
Yeah.
Yeah, the Hawking temperature should be in the denominator. I apologize. Yeah, my apologies. Yeah.
Okay, in which part of the room is that?
Shit. Which thing I thought I had this. Thank you to Isar, by the way.
No problem.
However, it's Natalia had it this way. Yeah.
Because the internet is not working on my computer. Because there was this quantum there, but I don't know.
You don't have.
This one is
Can you use
working
my.
at 6:20 where I need to like there's a Zoom link we need to go to. So
Yeah, but.
like, connect.
Yeah, exactly. Why not? The only thing is that they close here at 7 p.m. now.
It's almost at 7:30.
Hmm?
The download time was 7:30.
So it's 7:30, okay. Hello? Send me the slide, right?
Yes.
I'm gonna charge.
Right. So because
Yeah, okay. The second one is the correct one, right?
Yes.
Mhm. Yeah. Mhm. Okay. Why? You have this.
The internet that's here.
Yeah.
Then
Tama, we have something.
So we will be using this computer or okay.
Completely forgot. I'm sorry. I'm gonna be back in 5 minutes.
get the mic. Because that one has the line and it works. Yeah. Okay. Good evening to everybody. I would like to thank the organizers for this beautiful event. I'm glad to be here. And I'm Sebastiano Tomasi. I'm a PhD student at the University of Camerino. And this evening I will be presenting the work that I've done with my supervisors and collaborators during this year. My supervisor are Professor Orlando Luongo and Stefano Mancini, while another collaborator, which is in both of these works that I show you, is Alessio Belfiglio. And today I will be presenting entanglement entropy in quantum black holes and gravitational collapse. So two different background spacetimes, and we compute the same thing, so entanglement entropy of a field theory. Okay, so I will briefly introduce what is entanglement entropy. Then I will introduce what are black holes, quantum black holes, and what quantum black holes are supposed to solve, which problems they should solve. And then how black holes are connected to the area law. Then I'll tell you the method for computing the entanglement entropy. And then we will specify more clearly the background spacetimes, and then I'll present some of our result with some perspectives. Okay, so to introduce entanglement entropy, just a brief reminder for everybody. So we can consider this quantum lattice, which is found in its ground state. So the density matrix, it's the density matrix of a pure state. And if we want to focus on a region of like this shaded region, which is a closed volume V, what we do is we trace out everything else. So we get this reduced density matrix. And then the entanglement entropy is defined just as the von Neumann entropy of the reduced density matrix. Okay, now what are quantum black holes? Okay, nobody knows what quantum black holes should be, but it is widely believed that the classical description is unsatisfactory for some reasons, which I'll briefly mention. So the first one is the most obvious one, is that general relativity does not include any quantum effect. And that's kind of strange because we know that our best theory of matter is quantum field theory. So in general relativity, there is no mention of any quantum effects of matter. So we know that the description is at least limited. But of course, to solve this problem, we will need quantum gravity. And to date, we have no clear indication of a quantum gravity theory. So one of the problems, for example, is the presence of an essential singularity in some solution of the Einstein's field equations. Here I've reported the most simple one, the Schwarzschild solution. And you can see that for r equal to 0, so in the origin, we have this singularity, which is called essential because it does not exist a reference frame in which this singularity disappear. On the contrary, the horizon singularity, we can choose a frame in which the horizon singularity vanishes. So the horizon singularity is not essential, while the central singularity, since cannot be removed by any coordinate transformation, is called essential. And this poses a challenge from the quantum perspective because all the matter, according to this model, is condensed into a point. So it's clearly violating some uncertainty principles and quantum principles. Then I'll briefly mention the information paradox, which in general states that gravity can spoil the unitary evolution required by quantum mechanics. So those are just some of the problems and the motivation for considering attempts to quantum black holes. Okay, now, how are black holes connected to the entanglement entropy? The most important connection point is due to Bekenstein and Hawking, and they attributed a classical entropy to the black hole, and they found that the entropy is proportional to the area of the event horizon. Okay, so to the surface of the event horizon, and that's called the area law. In a completely different setting, So considering a quantum scalar field theory propagating in Minkowski spacetime, if we consider an inaccessible region of surface area A, and we then exclude the information in this region, so we trace out it, we obtain for the entanglement entropy a formula which is analogous in form. The coefficients are different, but is still an area law. So this is quite interesting, since it hints that maybe we could think about the black hole entropy as the number of quantum states in the interior, and that could bridge the gap, so to say, between a small bridge between the quantum theory and the general relativity. Okay, so how we actually computed the entanglement entropy? So we start from the action of a scalar field theory propagating curved spacetime, and then we define the Lagrangian. So here we have the general metric, we left it unspecified, and we also considered a non-minimal coupling, which will be important in one of the cases we consider. Okay, so now we have to specify this background. We did two works, and in the first one, so we considered static, spherically symmetric, quantum corrected metrics. So those are metrics like with this form, with a lapse function f. And this lapse function is designed to take into account, in some way, quantum correction to the that are due to quantum effects. So, for example, we considered the coherent quantum black hole metric from Casadio, and they proposed this modification to the standard Schwarzschild lapse function, introducing this term, and they have a nice paper that you can learn about this, how this came up. Okay, and this one, yeah, and this is one of the proposals, and we considered also other proposals, but I'll focus on this one. Okay, then the other spacetime we considered is a dynamical one, so it's not anymore static. And it's a model for gravitational collapse, namely the Oppenheimer-Snyder model. So the hypothesis of this model is to consider a uniform sphere of dust, homogeneous, which collapses under its own gravitational pull. So it's a very simple model, but it contains the main features of the gravitational collapse. So the formation of the horizon, which is this line called H+, and the eventual ending of all world lines into the singularity at r equal to 0. So this line represents the world line of the surface of the matter sphere, and eventually it collapses. In this model, the exterior is Schwarzschild, as we know from the Birkhoff theorem, and inside we have a Friedmann-Lemaitre Robertson-Walker metric with a positive spatial curvature, which is related to the density of the dust cloud. Okay, now I've told you the general setup, so the scalar field theory on one of those two backgrounds. Now, if one tries to compute directly the entanglement entropy using quantum field theory, one gets divergence, the ultraviolet divergences. So to overcome this problem, there are many ways. The way we employed is to discretize the Hamiltonian. And the discretization is two-step. So in the first step, we discretize the radial variables through this standard spherical harmonic decomposition. And then we discretize also the radial variable with this B, which is the cutoff, which limits the maximum energy and renders the entanglement entropy finite. So what happened when we discretize? For example, in the quantum black hole backgrounds, so in the static cases, we can, the Hamiltonian becomes equation 3 quite generally. And then from this Hamiltonian, which is just a system of coupled harmonic oscillators, we can compute the ground state by solving the Schrödinger equation. And the result is this density matrix we see is a Gaussian state, for which is well known how to compute the entanglement entropy. Okay, in the other case, the final form of the discretized Hamiltonian is this one. And you can see that now we have time-dependent coefficients. So very similar to before, but now we have this time dependence, which complicates things a little bit. And the time dependence is all due to the expansion of the contraction, in this case, of the background. So in this case, to compute the ground state, we have to solve this Ermakov-like equation, which is quite complex since it is nonlinear. But if we can find a solution, then we are able to write the ground state as a product of those wave functions. And here it is the solution. You have to plug the solution in here, and you have the ground state. The most important difference between the static case is this imaginary unit, because it complicates the procedure to compute the entanglement entropy, and the result in a strange feature you will see later in a moment. Okay, but nevertheless, the entropy can be computed, and so we computed it. Okay, here I'm showing the results for those two cases, so quantum black hole spacetime and on the left, and the other case on the right. So in this case, we compute how the entanglement entropy scales with the surface area. Okay, so to see if an area law holds, and we found that there are deviations from the area law near the origin only if the coupling is non-zero. Okay, so if the non-minimal coupling case, we have just the usual area law, while for strong couplings or for non-zero couplings, we have deviation near the origin, and we found them near the origin. For example, here I use those results are obtained for the coherent quantum black hole metric, and this metric like solves kind of solves the singularity issue by rendering forces experienced by matter finite everywhere. So even if there are some divergences in the metric we used, it fixes a little bit the situation. So we expect that since it solves the singularity issue, we expect to see deviation around here, and in fact we saw. Then during the collapse of a dust sphere into a black hole, we computed the entanglement entropy as a function of time. And an interesting feature is that, as you can see, those are the shells. The shell are just the radii that we choose that we have chosen for the traced out region. So, for example, here we traced out a small region for n equals 2, while for n equals 25, we traced out a large region. And you can see that the time dependence of the entropy does not depend so greatly on the size of the traced out region. So that's an interesting feature. Then another important feature is that near the collapse, which happens around here, the entropy diverges, and this is generally expected. And this strange feature in the middle, where the entropy decreases and then increases again, is attributed to this term, which is highly oscillating, and thus it produces this strange behavior here in the middle. Okay, so to conclude, I've shown you the work that I've done in the two papers. So the first was RLO in quantum black holes, which is published, and here we found deviations near the origin, which depend, of course, on the quantum model for the black hole we are considering, and we also considered some regular spacetimes like Hayward. Then the other work is this one, which is under final revision. And in this one, we computed the entropy as a function on time, as I just showed. And then we also looked at the entanglement entropy scaling in terms of the area to see if an area law holds, and we found deviations attributed to the non-zero spatial curvature. Okay, to conclude, some perspectives are that we could compute the area law in more quantum spacetime models. Then we would like to consider other aspects of entanglement by computing the entanglement degradation, and then maybe facing the information paradox with quantum black holes. Okay, thank you for your attention. I cannot hear what you're saying. Sorry. It's like echoey, yeah. No. Okay, try to leave the microphone. Yeah. Yeah.
So in log with log is a constant time. This
Yeah. Yeah, we scale the entropy just to make them all unity here, okay? Because they were like how do you say? Okay, maybe one if you start from a bigger shell, you start from a bigger initial entropy. Okay, so for example, the n equal 25 curve will start like here and do its thing. So we just shifted them down and made them all coincide there. So you can do a fair comparison between the time dependence between them. Okay.
Thank you.
Yeah, perfect. Grazie.
Ah,
Sì. How it works?
This is for the microphone. Yeah.
So that's I don't need this.
Is that mic okay for you? The one with the, it sounds a bit better, this mic.
So I use this.
Yes.
So I move there.
That,
And we have pointer? No. I have to yeah, if possible. Okay. Okay.
tell us about the quantum entanglement of 2.3 modes in the computer space.
Hello. Good afternoon, ladies and gentlemen. For me, it's a great pleasure to be for the first time in Napoli, in this fabulous city, and in this famous university. I will present a subject connecting the behavior of quantum correlations, in particular quantum entanglement, in a special space of relativity, namely in de Sitter space. The main ideas of my presentation consist in showing the time evolution of a Gaussian quantum entanglement of two bosonic modes associated with the scalar fields in de Sitter space, and at the same time in interaction with an thermal environment. And I will show you that quantum entanglement strongly depends on the squeezing of the bimodal states, on the parameters characterizing the thermal environment, namely dissipation, temperature, and also on the parameters characterizing the de Sitter space, curvature, and parameter mass. It's a special situation when entanglement is minimized in two special cases, when the mass parameter is equal to 1/2 and 3/2, corresponding to a conformally coupled scalar field, respectively minimally coupled massless field. I will very briefly describe the problem of quantum field theory in the de Sitter space. And in this theory, they introduced this special quantity, which is called mass parameter, and the parameter of curvature. In this description, when parameter p approaches 1, then the effect of curvature starts to be visible. And in the limit, when parameter p tends to 0, the curvature tends to infinity, and in this case, we will show that entanglement cannot resist, cannot persist. Bunch-Davies vacuum for a global observer, Alice, which is situated in this space, connects two open charts describing the Sitter space. Namely, they are named R region and L region, and this Bunch-Davies vacuum can be expressed as a two-mode squeezing state of these two regions, R and L. In this case, if we start with observer Alice, which is situated in the Bunch-Davies vacuum, and we have an observer Bob in the R region, by this operation, it appears ideally an a third observer, anti-Bob. So, starting with two observers, Alice and Bob, due to this property of amplification channel, we face three observers: Alice in the Bunch-Davies vacuum, Bob in the R region, and anti-Bob in the L region. By considering an initial Gaussian state of Alice and Bob, we describe in phase space, we have a situation in phase space which can be described by Gaussian states. And the formalism of phase space, it's very nicely described by covariance matrices, whose elements consist of first moment of operators of quadrature and second order operators. And so we can write analytically the covariance matrix of the three observers, and having in mind that region R and region L are causally disconnected, we have to trace out the unphysical mode, namely the anti-Bob. And so we obtain the covariance matrix, a physical covariance matrix describing the two modes, Alice and Bob. These facts that I presented until now are very well known in the theory, in the quantum field theory describing the de Sitter space. Now, the calculation that I made with my student consists in describing the evolution of entanglement initially existing in for the two modes, Alice and Bob, in interaction with a thermal environment. So we move in the framework of theory of open quantum systems, which is very well described by an axiomatic theory. Probably you know very well the axiomatic theory of open quantum systems is described by a Markovian-Marcer equations called Kosakowski-Lindblad, or including all the names of physicists that contributed to the demonstration of this Marcer equation: Gorini, Kosakowski, Sudarshan, and Lindblad equation. This theory is based on a very famous property named complete positivity of quantum dynamical semigroup, which describes this property of irreversibility in time. So we start with a squeezed vacuum state for Ellis and Bob. We introduce these states in the theory of open quantum systems, and we can study the evolution, we can investigate the evolution in time of the entanglement of Ellis and Bob, considering that at infinity of time, the state is like usually a Gibbs state, equilibrium state. So, as a measure of entanglement, we use logarithmic negativity, which can be expressed in terms of so-called symplectic invariance, which can be calculated from the covariance matrix written in the block form. And I will show you now the behavior of initial entanglement of Ellis and Bloch during the interaction with the environment. As expected, entanglement is decreasing in time due to the dissipation of environment. Entanglement decreases also by increasing the temperature of the environment. And you see that at some moment of time, if we have an initial finite entanglement disappears in a finite moment of time. This you know very well. This is a famous phenomenon of entanglement sudden death, which is already known in the theory of quantum correlations. So everything is almost evident that it's not nothing spectacular. At the same time, the squeezing of initial states, of bimodal initial state, increases the entanglement. Now, in connections with the dependence on the parameters characterizing the Sitter space, we can see that entanglement, as I said at the beginning, entanglement is minimized in two special cases. When nu, the mass parameter, is equal to 1/2 or to 1/3 corresponding to conformal field and respectively to a massless field. Entanglement is decreasing by increasing the curvature of the Sitter space. This means that by decreasing the parameter p. So the general feature of this model is that there is a strong competition between several parameters characterizing the system, namely parameter of squeezing of the initial state, the parameters describing the thermal environment, dissipation and temperature, and the parameters describing the Sitter space, namely curvature and mass parameter. And depending on the competition of these 5 parameters, entanglement can survive longer or shorter in time. The obtained results show the importance, the relevance of parameters in the Sitter space in connection with possible application in protocols of processing or transmitting quantum communications. I would like to say that a similar behavior, it happens in another model, namely in the Schwarzschild background. and where there is another situation. Hawking temperature also destroys the entanglement. Thank you very much.
Thank you for the interesting talk.
One of the first slides for your results, you showed the logarithmic negativity becoming negative.
No, logarithmic negativity. The expression of E n logarithmic negative can be positive or negative, but by definition, logarithmic negativity is defined as the maximum between the positive value of this expression and zero. So we have entanglement only when logarithmic negative, this expression is positive. When it becomes zero, the state becomes separable. So this expression for negative values does not have any sense. Mhm.
Question. So when you're talking about the entanglement entropy of some states between Alice and Bob, do you consider only pure states, or you also allow mixed states between Alice and Bob?
They can be also, yeah, very good question. The initial state can be, the initial state in our case is a pure state. It's a pure state because it's a squeezed vacuum state, but it can be taken as a squeezed thermal state, which depends in addition on the so-called thermal photon numbers. And if we start with such a squeezed thermal state, the entanglement has the same so squeezed thermal state can be separable or entangled depending on the values of average thermal numbers and squeezing parameter. But if we start with squeezed thermal state entangled, then again entanglement disappears in a finite moment of time. So we again have entanglement sudden death. Thank you.
Thank you very much. In that case, let's thank again our speaker.
Sorry. So I forgot.
No,
I think it's projecting it.
yeah, but I don't know where it comes. Okay, now let me see. Oh, happened. No, no, it's happening.
That's strange.
No, it's strange because I haven't checked. Okay,
No, it seems that, yeah, try to reset it. Okay, now it's going. Seleccionar nueva opción.
No, it was
Okay, yeah, now it should work. Now it's applying. Perfect. May I put your mic?
So next speaker is
Yep.
Thank you very much. For those who don't know me, yeah, I'm Álvaro. I'm a PhD student of Luis Garay and Mercedes Martín Benito. Although, wish me good luck because I'm defending in 2 weeks my thesis. And today I'm going to talk about superradiance, a project that I did in collaboration with Professor Elizabeth Stanley at the University of Sheffield. And, well, first of all, let's talk about classical superradiance. Classical superradiance is always thought about the effect that happens when you have a rotating black hole and then you put some incident radiation, and then the black hole emits more radiation than the incident one. Okay, so that's classical superradiance that happens for bosonic fields and in rotating black holes. However, today I'm not going to work with rotating black holes, but with charged black holes. But with charged black holes, a similar thing happens. Just that instead of losing angular momentum and energy, so that the black hole exposes this radiation, what it loses is charge and energy. Okay, but just a similar thing happens here. Classical superradiance. However, as I emphasized before, we need bosons because if we put fermions, then we do not have classical superradiance. And we are going to work with charged black holes and fermions. So basically, we do not have classical superradiance. However, our question is, do we have a quantum analog, a quantum counterpart of this phenomenon that acts in a similar way? That acts, for example, let's think what we are going to prove in this talk is basically that close to the event horizon of a charged black hole, there will be a spontaneous particle creation of particles that will lead to the discharge and the energy loss of the black hole in a similar way as it would be in a classical superradiance phenomenon. But everything here would be purely quantum effect. Okay, so this is just a brief summary full of the spoilers. But now let's get into the details, okay? But this is what we want to prove in the slides. Perfect. So let's first talk about the ingredients that we need for describing this quantum effect. So what we need, first of all, is a curved background, the resonant nostrum black hole, that has two different horizons. We are going to focus for describing these effects into the outer region, outside the event horizon. That's where superradiance happens. Okay, so basically, superradiance is going to see the black hole as a scattering potential. So that's why we're not interested in the region inside. On the right part of this slide, I show the Penrose diagram corresponding to this outer region, okay, the relevant region for us for describing this phenomenon. Perfect. So now, let's analyze the situation classically to show that we do not have classical superradiance. Well, let's put on top of this curved background a massless fermionic field. And then let's set an input, unit flux of a plane wave from sky minus, from the asymptotic region very far away from the horizon and in the past, with frequency omega. Remember that this black hole is static, okay? So basically, we put this input of unit flux, and then let's see what happens with the unit flux. As time passes, then this initial input mostly becomes reflected back again to the asymptotic region with a reflection coefficient r sub omega. But then we could have some part of the incident radiation that gets transmitted into the horizon with a transmission coefficient t, okay? But however, look at this because this is very important to understand the phenomenon. Although in sky minus and in sky plus we have plane waves with frequency omega, look at what happens when this radiation comes closer to the event horizon in H minus and in H plus. Frequency is shifted, okay? So basically, what we have now are plane waves, but with omega plus a shift. And this shift is given by the interaction between the charges of the fermion field and the charge of the black hole. Okay, if we wouldn't have charges, I mean, if there wouldn't, if there we wouldn't have this interaction between electromagnetic interaction, then we wouldn't have quantum supervariance. We are going to see that. But classically, establishing the relationship between the reflection coefficient and transmission coefficient, we find that, which says basically that the reflection coefficient cannot be larger than 1, and then as we had initially a unit flag of radiation, we do not have more radiation emitted by the black hole than the incident one. Okay, so this is a proof, well, the result actually, of that there is no classical supervariance with fermions. However, let's construct a quantum theory to discover if we have quantum effects. Okay, so just to remember, to construct a quantum theory, what we need is to do 2 steps, and both are necessary. First of all, we need to find an orthonormal basis of solutions to our direct equation. And second of all, which sometimes it's implicitly made in the literature, it's splitting the Hilbert space of solutions into one part of the solutions which are going to become our one particle Hilbert space, and then of the other part of solutions which are going to be related with the antiparticle sector. Okay, so this third step is what we are going to do right now. Perfect. First of all, the easiest part. Well, choosing an orthonormal basis of solutions. Well, we need to provide initial conditions in an entire Cauchy surface, which will be composed by H minus and SY minus. Remember that we have massless terms. And then the first part of these modes that will compose the basis will be the in modes. These in modes basically are, as I showed you before, okay? Unit flags coming from SY minus. But we need to have other type of modes, those that go out and going outwards from the event horizon, that are called the up modes. And we need both modes for describing an entire complete basis of orthonormal solutions. Okay, and basically these up modes also get transmitted and reflected. Okay, so once we have this orthonormal basis of solutions, we need to decide what we are going to call particles and what we are going to call antiparticles. And yes, I'm always talking in terms of choices because we need to choose, because we have inherent ambiguities in the quantum theory in terms of space-times. Okay, so basically this is our choice, which makes sense. Okay, for the in modes, what we do is to say, okay, let's call particles to those with positive energies in the asymptotic region, in SY minus. Okay, so then we choose omega positives for particles, omega negatives for holes, and then later antiparticles. And for the up modes, what we do is a bit stretching principle, but actually it's a natural thing to do. Let's do now as in H minus, what we have, the relevant wave number is omega tilde and not omega. Let's say that particles will be omega tilde positives and antiparticles omega tilde negatives. But this is a choice, remember. And then later, let's talk just a bit of a different choice. Okay, so if we do this, then we have a quantum field operator, just operate, in constructing expanding the field and constructing the annihilation and creation operators. And this defines then quantum state that we called the in quantum state. This in quantum state has a physical property. And this physical property is quite clear. As we have defined, this in quantum state is empty at SY minus, asymptotically far away from the horizon in the asymptotic path. So the question now is, okay, is it empty in SY plus? If it's not empty, then we would have spontaneous particle creation, and then we would have quantum supervariance. Okay, so basically that's what happens. We have computed the number of particles and antiparticles created at SY plus in our quantum state, and what we have found is that this number of particles is related to the transmission coefficients. And indeed, we have particle creation in a very low frequency interval. Okay, outside that interval, suppression of the particle creation. I mean, there's no particle creation. And this particle creation, as you can see in the figure, is enhanced when we increase the electromagnetic interaction between the charge field and the black hole. Okay? Now, just briefly, what we also can do is to compute expectation values of other observables, for example, the charge currents and the stress energy momentum components, so that we can prove that the black hole is both discharging and losing energy. Indeed, we found a region close to the event horizon that we have called, what it's called, the effective ecosia in Scala case, and there we have negative energies. So this name just reminds us of the ecosphere in curved black holes, in rotating black holes. Okay, so this just proves that we have quantum superradiance. Now, a brief comment about quantum vacuum ambiguities. Remember that I told you that we could have done other choices in the splitting of our modes. So what if we have decided that for the up modes, we have omega positive for the particles and omega negatives for the antiparticles? We could have done that. And the answer is that we would have obtained another state, the Boltzmann state. Okay, so basically the Boltzmann state is empty, asymptotically far away from the horizon, and then both in the past and in the future. So then it doesn't exhibit quantum superradiance. So basically we have quantum ambiguities, and this is not strange in quantum field theory, quantum space. Okay, so conclusions. Although a classical charged fermion field on a charged black hole does not exhibit superradiance, we have constructed a quantum state, the in quantum state, that describes both the discharge and the energy loss of the black hole. And this is then a purely quantum phenomenon, okay? But of course, the interpretation of this phenomenon depends on quantum vacuum ambiguities, okay? So thank you.
Thank you for very nice.
Thank you.
Yeah, I was just wondering, I know you just not really know, but so here you're doing some like what you're not saying, and looking at the part of like spontaneous figures. So isn't it? You call it quantum sporadians, but I wonder how different it is from sort of figure event. I mean, I don't know where's the line, if there's a difference or not. That makes sense to me.
Yeah, my thesis is about the Schwinger effect, one of the things that okay, so I call this quantum superradiance, but I have exactly the same question as you. I mean, I think it's kind of a Schwinger effect. I mean, you have an electric field here, an inhomogeneous quantum effect, Schwinger effect, but it's constant in time. So basically, I think they are both names that could. I mean, if someone has a different answer, I would like to talk with that person, because I don't see any difference actually. But normally, it's said in this context. It says it calls quantum superradiance, but
For what you counsel.
Let's think about it again.
Mhm. Repito. Eso sí que ya se me dio.
Right, I'll play this.
Oh, yeah, we're going.
With the knife? Am I ready?
Sí, tú, ¿verdad?
Knife. Oh, yes. Gotcha. Thank you. Hello.
That's about Good space.
Okay. So I will be talking about the extension of the computational quantum field approach to curved spacetimes. Indeed, when particle number is not conserved, we need a quantum field approach. Like, for example, in studying the Schwinger effect, which is the creation of pairs of particles and antiparticles when exciting the vacuum by strong electric fields, and also in Klein tunneling, which is the undamped wave packet propagation through potential barriers whose energy is higher than the energy of the incident wave by more than mc squared. So although Klein tunneling was firstly studied in first quantized theory, but since we have such high barriers, we expect to see the Schwinger effects. Moreover, some paradoxes appear when we study the Klein tunneling in the first quantized theory, and computational quantum field theory helped us to resolve those contradictions. This computational quantum field approach has been successful in studying the Schwinger effect, the Klein tunneling, and the regular tunneling. Yesterday, in the talk of Alex Maskin, he showed our results in studying the regular tunneling using this approach, and we showed that microcausality implies that no superluminant propagation is exhibited by the propagation of wave packets of fermions or bosons. Since this approach is used in studying the pair production in strong electric fields, we thought of generalizing this approach to see the pair production in strong gravitational fields, and so to extend it to curved spacetimes. Here we see the results in studying in flat spacetime, the pair production of fermions when we have a potential barrier. So we see the number of created fermions increase, and the narrower the barrier, the faster the saturation of a creation. So the number of created particles reach a saturation value, and the narrower the barrier, the faster the saturation to happen. In the case of bosons, on the contrary, the narrower the barrier, the faster the creation to happen. So we have a faster exponential creation. In the case of Klein tunneling, we see that we propagate a wave packet, while we can also account for the creation of pairs of particles and antiparticles. In the case of the Klein tunneling, if you study it in the first quantized theory, you find that your wave packet, when passing through the barrier, it is divided in two parts, and inside the barrier only negative energy solutions exist. But since the charge is conserved, both parts should have the same charge. So we have negative energy solution but the same charge, and this paradox was resolved in the computational quantum field theory, because we showed that the solution inside the barrier, this density calculated inside the barrier in the first quantized theory, is exactly equal to the reduction of the antiparticles number inside the barrier, those antiparticles which are created. So their number is reduced by exactly the same density we see in the first quantized calculations. And now I will show the formalism of this computational quantum field theory in curved spacetime. First of all, we need to rewrite the Dirac equation or the Klein-Gordon equation, but I will talk only about the Dirac case. We need to rewrite it in curved spacetime. This means to rewrite the partial derivatives as covariant derivatives, but also to be careful about the gamma matrices, which should be rewritten in those curved spacetimes. And writing the partial derivative will result as covariant derivative would result in this connection. And here we have our gamma matrices written in terms of the flat spacetime gamma matrices and the tetrad. And those guys called the tetrad or the Wilbein connect the flat spacetime to the curved spacetime. And the connection omega is written in terms of the commutators of the flat spacetime gamma matrices, and the spin connection, which is written in terms of the tetrads and the Christoffel symbols. To make this long story short, we just need to rewrite the Dirac equation in curved spacetime using these differential geometry tools. And finally, we need to write the equation in a Schrodinger form to be able to calculate the time evolution of the states. So this is the first ingredient, which is the classical field equation, which could be the Dirac equation or the Klein-Gordon equation. And then we need to quantize this field by writing it in a mode expansion in terms of creation and annihilation operators. But we need to be careful about the mode expansions we choose, because different mode expansions give answers to different questions, and those questions can be irrelevant if we choose our mode expansion in a wrong way. And finally, we write our quantum field Hamiltonian, which we will use to calculate the time evolution of our field operator. And in order to obtain this time evolution, we need for sure to use the anti-commutation relations of the field operator, the fermionic field operator here. And so the idea of this computational quantum field theory is to calculate the quantum field, the time evolution of a quantum field states and the quantum field observables in terms of calculating the time evolution of the first quantized states. And in order to do so, we calculate we have the Heisenberg equation to calculate the time evolution of the field operator. And if we do this calculation, we obtain the first quantized operator multiplied by the field operator. And this enables us from writing the time evolution of the creation and annihilation operators in terms of those amplitudes which are calculated in a first quantized as first quantized quantities. We have the modes, time evolution of the modes, and the projection on our mode expansion. So all the calculation is reduced to operator algebra and those amplitudes. So now we have our time evolved field operator. We can calculate from it the charge density or the number density of positive energy states or negative energy states, and we calculate those observables as expectation values, either in the vacuum or in the presence of a wave packet if we want to study the time evolutions in the presence of already existing wave packets. The numerical treatment is first to discretize space-time. So we have our position lattice corresponding to reciprocal lattice, and we evaluate if we have some electric potential or whatever spatial dependent potential. We evaluate it on the position lattice, and we evaluate the modes on the momentum lattice, and then we calculate the time evolution using the time evolution operator, and we use the split operator when we have terms depending on the position which do not commute with the momentum. So whenever needed, we use this split operator method. And finally, we use this time evolution operator to evaluate those amplitudes of the modes. And now some illustrations. We used a Schwarzschild-like metric in 1+1 dimension to rewrite the Dirac equation and then to calculate the Hamiltonian. And in this we introduced in this curved space-time, we introduced we looked at the time evolution of the vacuum states to see the pair production. So we saw the created electrons evolving in time. Initially, we have the blue line, and then we have this red line. So this number was obtained only because introducing this curvature in space-time without any potential. And then we can compare the growth of numbers of with different widths of the curvature. So we saw the narrower the curvature is, the faster the saturation to happen, similarly to what we have in potential barriers. So to summarize, we extended the framework of computational quantum field theory to curved spacetimes, and we are now employing this tool to investigate the dynamics of wave packets propagation and the pair creation phenomenon as well, including in the context of gravity analogs. And also we are employing this tool to investigate our phenomena in quantum mechanics, like entanglement of wave packets. That's all, and thank you very much for your attention.
So from field theory, how does it compare with the lattice-based methods and so on, which are
Lattice?
lattice
Okay. It is similar in the sense that we have discretized space-time, but it's so here we are not evaluating, for example, we do not have the structure of links, gauge links. It's what we have here are the modes of the positive and negative energy states, and we evolve those modes in time. So it's much simpler than lattice QCD.
Thank you.
Thank you.
Hi, thank you. I'm very happy to be here. It's also my first time in Naples, and I'm very glad to see some old friends and new faces. Indeed, I'm going to start from how to lose information. And most of the update will be not so much on where the information went. We had at least several good talks about it today, but being very pedantic. What does it take to consistently formulate the very possibility of losing information? And what are the consequences? Because they are quite varied and interesting. Okay, now let's see how we move. Good. So the story, everybody knows the story. I'll briefly remind you about it. It's best formulated by Bob Wald in his review from 2001, that if correlations between the inside and outside of the black hole are not restored during the evaporation process, we're in trouble. Some information would have been lost. I love English conditional tenses. It's also quite well known that for long time communities, open systems and say quantum field theory and curved background ran in parallel, because what Hawking represented as his superscattering operator using the dollar sign, honestly, is potentially nothing else than one of the particular completely positive trace preserving operators. How to deal with this? Over the years, I think we went through, or communities went through all stages of psychological coping with the problem, which include exorcism, denial, acceptance, grief, and embrace. And well, again, I'm not going to go through those stages with you, but let me show what are these topics that I would like to talk. I might be forced to cut at some of those points. First of all, I'd like to talk about the logical structure. We'll look at the paradoxes. Black hole information loss is paradox as other paradoxes in quantum mechanics. What does it take to build it? We convert those somewhat verbose requirements into math. So we'll see what are the black holes and what properties they should have to enable the paradox. We'll implement that in spherical symmetry and we'll get some of the interesting results. And if we have time, we'll talk about possibility of the observations. So where we are. Here are just some of the examples of very close links between Kabbalah, other mystic theories, and ER equals EPR. But more seriously, what are the ingredients of any decent paradox in quantum foundations? What we have is, first of all, now let's see that laser works. Yeah, we have classical ingredients, classical components, classical assumptions of the story. Then we have quantum results that we would like to preserve. And finally, we combine this, shake, mix, and either get the logical contradiction already, or it contradicts the experiment. This is the anatomy of quantum foundational paradox, and examples, of course, are EPR, Bell-type inequalities, Wigner-Friends, or firewall and black hole information loss. We assume reasonable things, get something which is totally unpalpable, and then have to choose our poison. For the black holes, we particularly need several things. We need the event horizon as our classical concept, and we need Hawking radiation. Now, what you have here is lifted by me from a paper by Hayward, and this is evolution of the views of Hawking on the existence of the event horizon, starting from it being totally, absolutely, undisputably essential property to something that maybe does not exist. How people deal with the information loss problem? Two views were in adjacent and competing articles, ranging from no by Don Marlon to so what, essentially, by Bill Andrew and Bob Walt. And more modern versions of the exorcism can be found in those reviews. So what do we need? And that becomes now useful and practical. To discuss the paradox, we need finite formation time, finite evaporation time. We need in states and out states. So we actually can lose information. We need event horizon. And again, we need it at finite time, not at the end of the day. We're not doing apocalypse, we're doing physics. Next, usual assumption, no drama at the horizon. At least the weakest form of the cosmological censorship is realized. And of course, we would like to have thermal or nearly thermal Hawking radiation to take something with low entropy to something with high. Now, let's look only at few of those properties and see how much traction we can get. And to this question, ladies and gentlemen, what is a black hole? People argue. Of course, we have this ancient manuscript. And by the way, the things in italic, it's not the abstract, it's the title. And in 2019, Eric Curiel wrote a very nice opinion piece in Nature Astronomy, where he interviewed different people who do black hole related stuff. And essentially, the common consensus about the definition was black holes is what I'm working on. More seriously, we need to take another ancient piece of wisdom and be careful with our definition. So we can have a traditional views on black holes, which following Valery Frolov, I will call mathematical black holes. And those are solutions of Einstein equations with the event horizon. Or we can have physical black holes. Those are trapped region of space-time, and we don't care whether they're regular or not, whether they're eternal or not. What we will care that they are here and now. So those are our black holes, trapped space-time domains. Well, of course, black holes have all kinds of interesting properties, and particularly, well, boundary of the trapped region, apparent horizon. And that's where we're going to look at. Now, another observation, if we stick to the logic, what can we have as an explanation? We have a zoo of exotic objects, and that's a very, very simplified picture. Everything that, well, we now know that we have to have the light ring, so the object should be sufficiently compact. To be more compact than Bogdal's limit, we need to violate something or have something exotic. But if we look at it again from the logical perspective, we can have three possibilities. Never-ending asymptotic collapse, like classical solution. Purpose-built ultra-compact objects with finite time or at asymptotic time compactness slightly bigger than the black hole of the same mass. Or to formulate, for example, the information loss, we need them to be formed at finite time. And it looks like an innocent requirement, but it isn't. So, rules of the game. 4 assumptions which are basically semi-classical physics. Moreover, we don't really care about the right-hand side. Even if I say energy momentum tensor, for us, whatever makes the left-hand side happy, the Einstein tensor, can go to the right. Renormalized energy momentum tensor, cosmological constant, higher order terms. At this stage, we don't care. What we do care? In practice, 3 things. Light trapping region forms in finite time of a distant observer. Its boundary is not too singular, and that means curvature scalars are finite. I don't require anything more than that. And the stuff is not too weird. Now, what is too weird in semi-classical gravity? Quantum theory allows a negative energy density, allows violation of the null energy conditions, but it doesn't allow arbitrary violations. There are bounds, quantum energy inequalities, and our solutions should live in peace with those bounds. So we take only these 2 ingredients of the paradox and look what it does to black holes. Now, just a little bit of motivation, because it's more motivational talk than anything else. Why finite time? Because that's sort of controversial. Again, you want black hole information loss problem, you need finite time. You want regular black holes which are transient, and you want something like this. By the way, I think those diagrams are not exactly right. You need finite time of formation. Oh yeah, and how many of you watched Interstellar? Do you like it? Yes. So you want finite time of formation of the outer marginal trapped surface. So this is the motivation. Now let's look at some of the implications. So because the time might be short, I will start with a high-level description of the process and the conclusions. So in spherical symmetry, we use Schwarzschild coordinates precisely because they are bad. They allow to get finite time. They give you all kinds of divergent quantities. We learn from field theory. We need to get a finite expression, so divergences have to cancel. From the way they cancel, plus the way that they use to solve Einstein equations, we can learn about the structure of the energy momentum tensor and the metric. And to improve our understanding of what's going on, then we will use null techniques. Properties of those physical black holes, well, finite infall time, not surprising if you have finite formation time. Again, spherical symmetry, black holes cannot grow. White holes, which come in pairs of solutions, can only grow. So you need interesting scenarios for the bonds. They're possible, but quite constrained. Well, collapse finite time, null energy condition is violated at the apparent horizon, at the outside, satisfied. If you have inner apparent horizon, then it's satisfied. Oh yeah, that's a nice bit. Parts of the popular models are not working. Surface gravity, very important. Most of the generalizations don't work because they give you either 0 or infinity or whatever you want. Kadama surface gravity works and causes some interesting troubles with black hole formation. If we look a little bit at how things are structured, that's what we do. Einstein equations, focus on the left-hand side, imposition of the two requirements. That's our logic. That's our logic. Going into spherical symmetry, general solutions in Schwarzschild coordinates, choice of variables. We focus, Einstein equations even in spherical symmetry are ugly. I don't think that many people will disagree. You want them to be as not ugly as possible. And this is what is achieved by using those effective components. Then we can write regularity conditions, and they're pretty nice and doable. Then we have nice Einstein equations, and things are generally nice. We can get classification of possibilities and the explicit expressions. Now I'll run through all this and go to the very, very end. So there was a lot of stories. I hope that you will read our papers and would like these stories. But let me just do the summary. Black holes are weird. If you really want them at finite time, you violate all four assumptions of the Buchdahl's, all four Buchdahl's assumptions. They're as exotic compact objects. Collapse may not happen yet because it's not cheap. Infaloss paradox, you need to work hard to formulate it. It's not clear it's there. There are interesting cosmological implications and interesting impact on quasi-normal. Now, if you are looking for a place, you have you've done your masters, you want to do PhD, come to Sydney. Well, I'm not that horrible. Surfing is good. Pay is not bad. Good people. Kangaroos. Oh, spiders and snakes, but that's minor. And many of those people, this is a collaboration on which the sun never sets just because of geography. I'm very grateful to, all people with whom I had luck to work. And thank you for your attention. Okay.
Does it work?
imaginary scene. Okay. Mm. Okay. So. Okay. Okay. Good afternoon. Yes. Sorry. Oh, please. Yeah. Thank you very much. So, as she say, I am talking about the role of entanglement and complete complementarity relation in QED scattering processes, and with a particular attention on the role that play the maximal entanglement that arise in this fundamental interaction. But before starting, let me give you some motivation. This topic represents a very active research area. Both because it gives a tool in order to study from another perspective the fundamental interaction. So in the context of high energy particle physics, it maybe represent a probe for new physics beyond standard model. And on the other hand, entanglement in those relativistic systems represent a possible resource in the context of quantum information, and we shall go to see why. This is only a few and partial list of the most recent paper that study the topic of the entanglement and other quantum correlation in the scattering processes. But let me introduce briefly the generation of entanglement in QED process. The first work by Cervera Lierta et al. Study how the entanglement in helicity at 3 level in the COM reference frame is generated in the low and high energy regime. Then this analysis was extended by Fedida and Serafini to the whole energy regime and for an initial mixture helicity state. And in order to be more precise about this setup, we have done the following things. The process is unitary, of course. And in the QED interaction, unitary is recovered if you put in your calculation the one loop correction that from arise the imaginary part that verify the optical theorem. But we have done another things. We have fixed the output angle by a POVM procedure, by an arbitrarily sharp filtering at a fixed output theta, the scattering angle, and theta by theta, we have, for each theta, calculate the entanglement between the output part. Okay? So, for study this phenomenon, we have report here as a paradigmatic example, the Baba scattering in the center of mass reference frame. And in order to begin to study the generation and distribution, we have considered this setup. Here we have two particles, electron and proton, Baba scattering, in which one of the incoming particles is initially entangled with another one that not participate directly to the scattering, a spectator particle. And we have calculate concurrence in this context between the three bipartition that we get after scattering. And that is what we have. We have a series of plots that resume our main risks. Depending on the initial entanglement weight, we have the blue line that represents the initial concurrence in the BC channel. And as we can see, the
fundamental interaction acts like a pump that sucks the initial entanglement in favor of A, B, or AC channel. But in the relativistic regime, at theta equal to pi, the fundamental interaction acts exactly at a quantum gate that transfers completely entanglement from the BC channel, where entanglement was present before the scattering, to the AC channel. That channel that is formed by that particle that never interact directly. Then, in order to understand better all these results that we have resumed there, we come back to the more usual and fundamental processes, the 2-in-2 scattering processes. And we study this setup with the aim of complete complementarity relation. What are the complete complementarity relations? From the famous concept of complementarity by Bohr, the first quantitative version of complementarity was built up by Wouters and Zurek and Engler, and they obtained these inequalities that are relating the particle characteristics to the interference particle characteristics. This is a quantitative version of the duality, the fundamental nature of a quantum system. Then Jakob and Bergu extend this treatment, this analysis, and obtain a very interesting things. For a bipartite pure state, this inequality saturates to this triality relation. And this relation is Lorentz invariance. The entanglement interplay with the particular characterization and the wave characterization, local wave characterization of our system. Then the question is how a fundamental interaction can mediate the interplay between the local and non-local characterization, deeper characterization of a scattering system. And can be this fact characterized more deeply, open a new window in order to study fundamental interaction? This is the question. So what we have done, the previous three quantities can be calculated as a function of the coefficients of a general qubit state. And what we have done was to start from a different initial state and evaluate how the fundamental interaction play with our fundamental aspect of our quantum system. And this is what we obtain, very briefly. If we start from a perfect factorized state that show only the particle characterization, the fundamental interaction, again, acts as a pump that sucks the predictability in favor of the no-local characterization, entanglement, and visibility, and in the ultra-relativistic regime, only in favor of entanglement. And this happens exactly if we start only with visibility, a state that shows a maximal visibility. The things is more complicated, of course, when we we start with an initial state that mix these two properties. But if we start with a state that is initial entangled before the scattering, we can distinguish three different regimes. One regime in which entanglement is grouped with respect to the initial one. Another regime that shows an opposite behavior, and a mixed regime here. Here we want to plot only how we can obtain a deviation from the Bell state, that is the black line, the horizontal black line, modified the entanglement parameter. Then, as I say, we can put on a point of a scattering parameter in which we can obtain a mixed regime. But the more interesting things is happen when we start with a maximal entangled state. If we start with a maximal entangled state, the QAD do anything. The interaction doesn't touch it. The maximal entanglement is completely preserved for all that processes that imply the same statistics, spin statistics particle. So fermion in fermion, maximally entangled fermion in maximally entangled fermion preserved maximally entangled. Okay? So in order to deeper understand this fact, we have studied, this is not happen when we consider two scattering partners that have a different spin statistic. And in order to understand deeper this fact, we have studied the spectral properties of the matrix, of the maps, of the quantum maps that characterize our process. And what we obtain is the following things. Those states that represent that are represented from Bell state or a convex combination of Bell state, a maximal concurrent state, form a maximal set that form an invariant set for that map that simulate the scattering. If we iter the process, the scattering process, n time with arbitrary n, the form of the maps have the same form, show the same relation between the ingredient of our matrix. And moreover, and remarkable, if we done an infinity interaction, we take the output particle and we recollect this and we scatter another time, infinity time, the entanglement saturate ever, always. No matter the energy regime, no matter the form of initial state, the entanglement saturate. The QAD interaction want to go to the non-local characterization in correlation terms. And this is only the Baba scattering form of the matrix, the functional structure of our Baba scattering matrix. As I say, the relation between the matrix elements are the same, no matter how many scattering you do. And the heart of the mechanism, the reason that stay at the heart of the mechanism is the following. The eigenvalues corresponding to the eigenvector of that matrix, the eigenvector are Bell state or combination of Bell state. And when you done n scattering with n arbitrary great, the eigenvalue that dominate corresponding to the eigenvector will be that eigenvalue that show up our maximal entanglement state as eigenvectors. And this is a plot that shows this mechanism. Starting from RL or RR state, we have a different physical situation. Here we have more velocity in increase our entanglement, and this is the little difference between a Moller scattering or the Baba scattering. So, and finally here we have want to show what happen if I do a random filtering. If I not fix at a fixed theta, but if I random choose every time a different theta, it saturates ever, because this is an intrinsic characteristics of our fundamental interaction. This is the global 2 minutes. Thank you. Okay, thank you. So this is the global behavior of saturation of entanglement in the non-relativistic regime. and in the relative X one. And here a little bit of conclusion. Entanglement with a spectator particle is the fundamental interaction of on the entanglement with a spectator particle at a relativistic regime, theta equal to pi acts as a quantum gate, the transfer completely entanglement, and CCR gives us a possibility to a complete characterization of generation and QAD, and conservation and saturation are the consequence of a deeper nature of our interaction. Thank you very much.
So, like, it's pretty interesting. And so, how do us?
How?
How do us? Do you think this sort of results applies in the election regime, QC regime as well?
Okay.
How do we
Okay, QD is a very particular and perfect theory that what can I say for now is that if you broke parity, you will not done this. But we are studying this phenomenon, and we have, of course, extend this for a more general initial state in order to be the interplay between the classical characterization. And so, for example, in that more general configuration, I don't know if we have a saturation. So you can change interaction, you can change the initial state, and I think that it can be a very good tool in order to study particular aspect of our fundamental interaction. Thank you.
Thank you very much.
Thank you.
You want to manage the Zoom meeting? Meanwhile, I'm going stop the stream, okay? Huh?
Let's start and share those.
Ah, yeah, I have slides. Yeah. I'm coming back in 1 minute. Just stop the stream.